Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, is an honor and privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside, guys, and we are going to be reviewing all of the fall semester for Integrated Math 3 material with a little caveat. There are going to be some things where I'm going to be doing some graphing square roots and cube roots in here in this material. However, if you'd like to see some stuff in what would be Module 11 with radicals, where it is using simplification properties with expressions of exponents and radicals, as well as solving radical equations, go and check out the description section down below. Immediately you will get a link to another video where we review modules 10 and 11 on graphing square roots and cube roots on top of doing some radical simplification of expressions and then solving radical equations. However, everything else here will be covered in a 50 question review. Now this is slim pickings compared to the 150 plus question review I did for Integrated Math 2. I don't know how much longer or shorter, this should be shorter than it, but I don't know how much more overwhelming this stuff should be. I'm going to play under some assumptions that you've seen some of my videos before, or you've seen me teach in some capacity, or at the very least you can pick up some of the things that I'm putting down when I talk about them. Now if you'd like to follow along with me with this, also down below in the description section you will find a PDF to the 50 question thing that I am doing, as well as, when I'm able to put them up, timestamps for each individual problem for all 50 problems on these. And I hope that everything here will be good and sound and accurate and very, very descriptive, as I tend to do. So without further ado, guys, I'm going to go ahead and get started with this one, and we are going to start all the way from number 1 here, where we simplify each expression. These are polynomials where we will be adding and subtracting and combining like terms and writing them in standard form and all that good stuff. So let's go ahead and get started. Number 1, simplify each expression. This expression, 3k cubed plus 7k squared minus 8 plus the quantity k squared minus 6k cubed minus 6. So our goal, of course, is to combine like terms. These are inside parentheses, really with no impact, given that this is a plus here. I can just as easily write this whole thing without parentheses, and like I said, there is no impact, provided that you maintain the signs that there were. We are going to add k squared. We're going to add negative 6k cubed, which means we're going to subtract it, cubed, and then we are going to add negative 6, which is subtracting 6. As far as combining like terms goes, you got to add things with matching variables and matching degrees. K cubed can add with another k cubed, or subtract in this case, and I want to do those first because I want to be in standard form. The highest degree of this polynomial is 3. So 3k cubed minus 6k cubed is negative 3k cubed. 7k squared plus k squared is 8k squared. Remember, that is a 1. K squared in that case, and negative 8 minus 6 is negative 14. And that is, of course, also in standard form, and we are done. Now, number 2 is the same kind of problem as number 1, with the one difference that this is a subtraction instead of addition. And it does change something because we are subtracting this quantity, not just 2p to the 5th, but also 8p cubed and 8, which means we are going to change these signs. As they are addition, they will become subtraction without parentheses. If they were subtraction, any of them, they would become addition. Subtracting a negative is a positive. Now these don't change. We are going to keep these the exact same way as they were. So 6p to the 5th plus 8 minus 6p cubed is going to subtract 2p to the 5th. It is also going to subtract 8p cubed, and it is going to subtract 8. Give me 1 second as I change. There we go. Okay, so right here I'm going to combine like terms, and I want to do the p to the 5th guys first. So 6p to the 5th minus 2p to the 5th will be 4p to the 5th. And negative 6p cubed minus 8p cubed is negative 14p cubed. And plus 8 minus 8 is 0, actually. So those are gone. Those, I don't always like to say cancel out, but, you know, they are eliminated for all intents and purposes. Now, you know, as long as I've taught this, I always do try and warn my students that once you start learning, like, the multiplication stuff down here, where you distribute through everything, students start to go back to these and go like, ow, let's distribute all these and multiply. Whoa, time out there. Be very, very, very careful. You are adding. Just because there are parentheses and just because you learn multiplication doesn't mean you do it here. You are adding here. You are subtracting here. Sure, you distribute the negative, negative 1 even as you multiply those, but these aren't multiplying, they're subtracting. So be very careful, read the problem, slow down, take a breath. And if you have this little space to work with, I doubt they're going to, well, actually take that back. Look at this little space they're asking you to work with as well. But anyway, just make sure that you're reading the problem for what it is. They do say, oh no, they don't say find sum or difference. I don't know what I'm talking about anymore. It's okay. All right, Numbers 3 through 6, we are going to find each product. This is where we multiply. As there is no operation in between, the implication is multiplication. So what I'm going to do in 2a plus 6 times 7a plus 1 is I'm going to distribute the 2a into the 7a and the 1. I'm going to distribute the 6 into the 7a and the 1. Multiply each term in one quantity with every term in the other quantity, and then we'll combine like terms where we do as well. When you do multiply a binomial times a binomial, sometimes this is also known as foiling. Multiply the first terms of each quantity, the outside terms, the inside terms, and the last terms of each quantity right here. You are not multiplying 2a with 6, you're adding them. You're not multiplying 7a with 1, you're adding them. Anyway, 2a times 7a gives us 14a squared. The a's multiply right there. 2a times 1 is 2a. 6 times 7a is 42a, and 6 times 1 is 6. Now, what I will generally do, what I would tend to do, and you're going to see me do this a lot more, is I won't write plus 2a plus 42a. I'll go straight into 2a times 1 is 2a, 6 times 7a is 42a, and I'll combine them outright, knowing that these will combine right here. In fact, sometimes I won't even say a. I'll say 2 times 1 is 2 plus 42, which is 44a. Right? We know that an A is going to happen when it comes to those things combining. Just a little small thing to be more efficient, and I think that's going to be very effective and important when I start talking about factoring quadratic trinomials. So get used to the concept of me playing with, if this is FOIL, the outside and the inside combining like terms and what they combine to, without necessarily me writing out what it is they combine to. That'll be an important tactic. All right, number 4, I think it is important for me to write these things out, though, because I will have to combine more like terms than just those, and there are 6 terms involved here. So here on number 4, I'm going to be distributing the 3n squared into 2n and 8, and I'll get 6n cubed plus 24n squared. Now I'm going to multiply negative 6n to 2n and 8, and be careful, it is a negative. Negative 6n times 2n is negative 12n squared. I think most people tend to get that one. And then you forget negative 6n times 8 right here. Sometimes people put a minus and they just go 6n. It's negative 6n times both of those. Negative 6n times 8 is negative 48n. And then negative 4 times 2n and negative 4 times 8 gives us negative 8n minus 32. Right there. And like I said, this is where you got to make sure you combine like terms in the proper way, everything that goes on. By the way, stay in standard form here. 6n cubed is first, 24n squared minus 12n squared is plus 12n squared. Negative 48n minus minus 8n is negative 56n, and then there's the minus 32. And all's taken care of. Good, awesome. Okay, number 5, 3a minus 4 times 3a plus 4. Now, I will do it in a practical manner, but in doing so, I want to iterate that this is a classic, a minus b times a plus b case of a difference of 2 squares. Not to confuse this a with this a right here. That's just the general form of how we tend to write this. This does distribute into an a squared minus b squared case, where you square the first term, you square the last term, and you subtract them. That will end up being the result. I will show you how foiling comes to be with that, and in future problems, I will not show the practicality. I will just go straight into it's a difference of 2 squares, especially when it comes to us factoring those. We have to know that that's what it comes up to be. 3a times 3a is 9a squared. 3a times 4 is 12a. That's added. Negative 4 times 3a is negative 12a, being subtracted. Negative 4 times 4, be careful, it's negative 16. And as you imagine, or as you can see what happens, 12a minus 12a is 0. Yeah, they cancel out. But you're left with 9a squared minus 16. Is that not squaring 3a and squaring 4 and subtracting that result? It indeed is, and that's what we're doing there. That's the a squared minus b squared. If you can recognize that's what's happening, then you can distribute straight into, sorry, not even distribute, you can pick apart those parts, square them, and when you square 3a, you are getting 9a squared from that. All right, number 6 here, 6b plus 3 quantity squared. This is the same kind of special case thing. It's not a difference of 2 squares or anything like that. That's not what it comes to be. It actually turns out to be what's called a perfect square trinomial, where if you have some a plus b value that's squared, it turns out to be squaring the first term, doubling the product of your 2 terms here, and squaring the last term as well, and adding all those up as a result. So I will do it in a practical sense the first time, and if there's any other time that it comes up, probably not through multiplication, but through factoring, I want to remind that, yeah, you square the first term, square the last term, you double the product, add them up, and you're good to go. So right here, in a practical sense, what you don't do, what I got to say right off the bat, straight up, is you do not just square 6b and you square 3. Right? There's a whole middle term here. So be very, very, very careful, especially on a multiple choice test. If it turns out that there's a 36b squared plus 9 answer, you don't select it. You got to be very careful now. You're going to get it wrong. So if you have to do it in a practical way, squaring something means multiplying it to itself. And as you saw in all the last few problems here in terms of foiling, there is not just the first two terms that multiply in the last two terms. There's a whole outside and inside portion as well that happen. 6b times 6b is 36b squared. 6b times, here, this time I'm going to do it straight up. This is 18b plus 18b, right? And that's where you get 36b right there. And then 3 times 3 is 9. So you can see there's this whole middle term here. And is this not a perfect square trinomial in this way? Again, not to confuse this b here with this b. This is not a perfect square trinomial where you would indeed square the first term, square the last term, and then double the product of those two terms, the 6b times 3. Why are you doubling it? Because you're doing 6b times 3 twice, right? 3 times 6b plus 3 times 6b. So you are doubling it up, and that is what happens in all perfect square trinomials. So 18 doubled is 36, and obviously these things happen here. Now, this goes without needing to necessarily write this. Of course, that's the whole idea, is that we can do that mentally, perhaps, as we process it. And of course, I wish that I had future problems where I can do it. I'm sure we're going to do it in some factoring, though, with perfect square trinomials. If you recognize it, you're good to go. Is there anything else I wanted to say to this one? I don't think so. I think that's it. All right, we are going to divide this one right here. N to the 5th minus 10n to the 4th plus 6n cubed plus 32n squared minus 46n plus 13 with n minus 9. Now, as long as it's a linear factor, I will attempt to use, with you guys, synthetic division, at least when it is a straight up linear factor in terms of a 1n minus 9 right here. It is very streamlined and very effective to use synthetic division. And synthetic division does the following. It ignores variables and degrees, provided that you are descending in order of degree from 1 degree to the next. 5, 4, 3, 2, 1, 0. Because as we write out these coefficients, 1, negative 10, 6, 32, negative 46, and 13. This doesn't see those degrees, so it's assuming you know what you're doing with your degrees here. And the bottom, the last term is the constant. So again, constant, linear, quadratic, cubic, quartic, quintic, right there. And that we use the root of n minus 9. By the root, I mean if n minus 9 were to equal 0, then n would equal 9. We're going to use the root, and I don't know if everyone draws it the same way here. This is how I draw it. As far as placing it right here in this little box, this is the thing that's going to multiply by the result that goes down here. Maybe I can even give you a tie-in, because I'm going to do long division with this as well, give you a tie-in as to how synthetic division works in tandem with the long division that's there. I'm going to bring down this 1 right here, and I'm just going to have a 1 right there. I'm going to add these two the two elements in the column together every time, but nothing's going to add with the 1. You'll see why in a moment. 9 times 1 is 9, and I'm going to add here, negative 10 plus 9 is negative 1, times 9 is negative 9. 6 minus 9 is plus negative 9, but 6 minus 9 is negative 3, times 9. Add these, you get 5 times 9. Add these times 9, and we get 4. Now, as we divided by a linear factor, we went from a quintic to dividing by a linear. We should now be down to a quartic, which means that this guy here represents the quartic term. This would become 1n to the 4th. And then this is the cubic term. This is minus 1n cubed. And then minus 3n squared plus 5n minus 1. And you're wondering, well, what comes next if this is the constant? This guy here is the remainder. That's not a 14. The 4 right here represents the remainder. And the remainder is added plus 4 divided by that n minus 9. 4 was a whole that could not divide by that n minus 9, and this is the part that remains. So this ends up being the division of this guy right here. That is your final answer. I don't know where to place it. I'm going to do long division right in this area where I have this answer. So I'm just going to go ahead and place it up here and see what I can fit down below, and we'll see if we can get matching answers there. Now I'll keep synthetic division there. Like I said, I'll do long division on this thing, and let's see if we can connect the dots as to why synthetic division works the way it does. It's a nice little magic trick, but it assumes a lot of things from you, the user, that you're going to do, which is, of course, use a linear factor, write these things in descending order of degree, literally from one at a time. You add these things up, provided that you give them the root, all this kind of stuff. So let's do long division on this guy, and we get n to the 5th minus 10n to the 4th plus 6n cubed plus 32n squared minus 46n plus 13. And let's divide that all by, I don't even know if there'll be room up there, n minus 9. So in long division, what do we do? Now, long division you can use every time in division. Synthetic division assumes linear factors, so you can't always use it. So make sure you know long division. N goes into n to the 5th, n to the 4th times, as in n times n to the 4th is n to the 5th. And we're literally going to multiply these two things and subtract out from here. N times n to the 4th is n to the 5th. Negative 9 times n to the 4th is negative 9n to the 4th. Now here's a part, if you haven't been with me before on this, or if you haven't paid too much attention to it, you got to be very careful, because this is an OCD thing and everyone's different with it. If you know in long division, you subtract the result of what's on top with what's on bottom, right? I grew up in a habit of not writing the minus. And with different terms, what I would have to do is I'd have to either have a minus this quantity, or I'd have to say minus here plus here. And a lot of people do that. A lot of people do that. I just know that I'm subtracting, and I don't change these signs. So please bear with me as I don't. It's a habit that I'm aware of and that I'm not ready to break for any reason, unfortunately. So be aware of it. Maybe pick up the same habit as I do when it comes to long division. N to the 5th minus n to the 5th is 0, as they naturally should cancel out with that. Otherwise, we wouldn't go down to the next degree. And then negative 10n to the 4th minus negative 9n to the 4th. Basically, add this now, right? Becomes negative 1n to the 4th, like that. And then I bring all these down because these are subtracting with nothing that can combine with it. So bring these down. And yeah, you know, I'm teaching some of the stuff as if you are kind of hearing some of it from me for the first time, because, you know, if my students even are reviewing from the stuff, you know, there's an assumption that they need to learn some of it. They're not just looking for the answer. Maybe they are, in which case they can fast forward through this. So like I said, I'm happy slowing this stuff down to get you to understand what I do. Especially, look, I'm going to divide again. So I want to make sure that you know how I'm doing it right the first time. N goes into negative n to the 4th, negative n cubed times, because n times negative n cubed is negative n to the 4th, which those will of course subtract. Negative 9 times negative n cubed is positive 9n cubed, and as we subtract right here, we get 0, as those things cancel, and then 6n cubed minus 9n cubed, minus 9n cubed is negative 3n cubed. It's hard when you've been teaching all day already to kind of go through your words. Okay, so that's what remains down here. And we can keep going. As long as n can keep going into your terms, as long as there is an n afloat here, n can go into it. Once only a constant remains, n can't go into that anymore. N goes into negative 3n cubed, negative 3n squared times. N times negative 3n squared is negative 3n cubed. Negative 9 times negative 3n squared is positive 27n squared. Subtract the results there. We are going to get 5n squared minus 46n plus 13. And I don't know if you do this, by the way, whenever I put the divided by, but that's what I'm doing. Now I'm doing this divided by n minus 9, right? Or at least the parts that remain. N goes into 5n squared, 5n times. It's one of those things where I even wonder if it was something that I was taught or if I just built the habit for myself. And I don't even know. I've been so far removed from doing this in school that I couldn't even tell you, to be honest. It's one of those things. I promise, or not I promise, I convinced myself that, like, I taught myself how to factor and, you know, graph and things like that, or that I picked something up along the way that wasn't even from my teacher sometimes, because I'm like, how did my teacher teach it? All right, n goes into negative n, just negative 1 times right there, as n times negative 1 is negative n. And negative 9 times negative 1 is positive 9, and 13 minus 9 is 4. N minus 9, n cannot go into 4 any number of times except for like that fraction number of times. 4 is our remainder. So this end result was n to the 4th minus n cubed minus 3n squared plus 5n minus 1 plus that 4 remainder of n minus 9. And that is the final result, whether you do it one way or the other. So let me just write the plus 4 over n minus 9 right there, either or. Now, how does synthetic division work? How given the tactics in long division, did someone create, and I don't know who it was, Mr. Synthesis himself, how did they create some version of this thing that I love, I enjoy? It's very streamlined, very fast, and it works. How do they do it? Well, given that they don't have variables, right, they are assuming that you're going down in descending order of degree. Now, if there was no squared term, if this didn't say plus 32n squared and it just wasn't there, you would have to put a 0, all right? That's part of the assumption things, that you are going down 1 degree at a time. And we know this because this is just an n to the first power. Again, we know it's an n to the first power. We can't use synthetic division if it's not. So how does synthetic division know that? Because you can't do it if it's not, and that's the big thing. So we know that's an n to the first power, right? So you do have to put things in descending order just like that, and we do know that this goes from an n to the 5th to an n to the 4th. That's one little trick. What's another little trick? Well, that this thing also knows that because it's a linear factor such as a 1n, it's not like 4n minus 9 or anything like that. It is a 1n minus 9. We know this because this root right here that applies needs to multiply not only that 9 in here, but n needs to go into these a certain number of times. N goes into n to the 5th, 1n goes into 1n to the 5th, 1n to the 4th times. That's why this 1 is here. That's why we bring it down. Whatever this coefficient was right here to start with, if this was a 4, it'll go into it 4n to the 4th times. That's why I'd bring the 4 down, because it knows it's a 1n that's going into it. It is that knowledge for that thing. Also, we add instead of subtract. Hold on, I need to take away these numbers here before I forget. We add here instead of subtracting because, remember how this was a negative 9 here? Well, now the root is the opposite sign of this as we added 9 over. So instead of subtracting here, given that a negative 9 was multiplying, now we're adding here given that a positive 9 was multiplying. So synthetic division is trying to make things streamlined and easier. We know that the subtraction here got messy, especially when I don't write a minus. But I don't need to write a plus here, and I think you're going to be happy in assuming that these are addition right here, knowing that we switch the sign given the root. So a lot of things are put into play under the assumption that this will work here. And you know, you don't always necessarily want to use synthetic division, all depending on the situation. Such as number 8, you can use it, but you got to be very careful about a specific situation. And I'm just going to move on to number 8 right here. Number 8, I'll use synthetic division, but you got to be very careful about something in this. First of all, no matter whether you use long or synthetic division, put this thing in standard form. 7v to the 5th. You got to go from kind of top to bottom with this. 7v to the 5th plus 13v to the 4th minus 65v cubed minus 54v squared. Oh, Jesus. Hold on. V squared minus 47v plus 11. Okay, so, and that is going to divide by this. But also, I want to rewrite this thing too. This isn't even in standard form. This is 7v minus 1. Now here's the thing. This may be a linear factor, but it's not the linear one in the way that it's not the linear factorization. I could factor 7 out of here, and I'm left with v minus 1/7. And that sounds weird for you to say and go and or look at and go, why did you do that, Mr. Robinson? Why did you force yourself into a fraction? Well, because do you know what the root of this thing is here? If 7v minus 1 equals 0, you add 1 to both sides, and you divide by 7, you get v equals 1/7. You know what the root of this thing here is? Also 1/7. But if I use 1/7 in my synthetic division, which I have to do, if I use 1/7 in my synthetic division, I'm not dividing this thing here by 7v minus 1. I'm dividing this by v minus 1/7, which means the 7 is not being considered in this division right now. So if you're going to use synthetic division, it has to be with the linear factorization version of a factor with a 1. It has to be. And that means that 7 still exists as something that still needs to divide in the end. That still has to happen. So you got to be careful here. You got to know how to take a 7th of numbers. And I hope that we're going to have numbers that we can take a 7th of and they'll be clean. I can't guarantee it, but I hope that that's going to happen, right? Well, I mean, listen, if it's not, then we would have the same fraction issues up top in long division as we would in synthetic division. Taking a 7th of a number is not too hard, guys. You just divide a number by 7. So instead of multiplying, you're dividing. But we're still going to have to divide by this 7 ultimately in the end. Now, why am I not dividing by 7 in the beginning? Because not all these coefficients can divide by 7 evenly. So I'm going to do that at the end. I can't forget about it, and then I'll use long division with the regular 7v minus 1 after. Okay, so my coefficients here are going to be 7, 13, negative 65. Make sure we're not skipping anything. V cubed, v squared, negative 54, negative 47v to the first, and 11. And synthetic division, ahoy me hoy, let's go. Bring down that 7, take a seventh of it, so divide by 7. And then you get 1. Add, you get 14. Divide by 7, you get 2. Add, you get negative 63. Divide by 7, you get negative 9. So these should be, good as far as dividing by 7 and such. And furthermore, these numbers hopefully divide by 7. It looks like they kind of do. Well, of course they divide by 7, right? I'm dividing by 7 right now with them. I'm not even thinking clearly about that. Divide by 7 right here, and you get negative 9 again. And then negative 56 divided by 7 is negative 8. And add those right there, and you get 3. So right here, and honestly, I guess as I look at it right now, and this wouldn't always be the case, maybe it would. Now I honestly, I don't use synthetic division very often with a thing like this. These numbers here are probably the numbers that you get when you divide these by 7. So you'll see. Anyway, so this ends up being 7v to the 4th power now, right? It was v to the 5th, now it's v to the 4th, plus 14v cubed, minus 63v squared, minus 63v, minus 56, with a remainder of plus, so that remainder of 3 plus 3 over, you got to be careful here. So far we only did v minus 1/7. At least I got to believe that that's what's happening here. Yeah, it is. Because now when I divide everything by 7 again, when I divide everything by 7, I'm really going to multiply by 1/7. And I say that because now the 7 gets to distribute back into here. You can see why synthetic division might not necessarily be the strongest thing here. And you do get v to the 4th, 1v to the 4th, plus 2v cubed. I'm dividing all these by 7. Minus 9v squared, minus 9v, minus 8, plus 3 over 7v minus 1. Because remember, the 7 distributes into here because it's a denominator value. And this should be our final answer here. Now, the thing I was mentioning here was that 1 is here, that 2 is here, that negative 9 is here. And I'm trying to think if that always happens, depending on what my root is. What if this was 7v minus 2? I don't know. I can't think that far ahead into it. Like I said, I don't always use this method. I more often than not would use long division for a case like this. And I don't even know where I can fit it. I'm going to go ahead and cut this little part off right here. Just give me one moment. I'm just going to kind of copy and paste this part of these last problems that you just saw down below so I can give myself more room for long division. Okay, so these will go right down there. Sorry about that. And I could just wipe these out from here as we do long division on the same problem, which is probably a fair thing to do. So on number 7, I like synthetic division. Oh, by the way, this isn't the answer yet. We're not just dividing. I'm going to state what we're going to do after this. I apologize for that. I've probably made that mistake before. But on number 7's division, what was I going to say? Why synthetic division would be my preference. On number 8's division, even though it's a linear factor, it's not the 1v kind of linear factor, so long division would probably be my preference. Unless I could have completely divided these by 7 to start with, and it didn't look like it was something I could have done. That being said, I wonder if I would have known if this was a factor off the bat based on that. That's okay. All right, so let's clear this out as well. Great. Okay, here we go. Let's do long division on this same one. I think I have to move these further down, I'm going to be honest. Give me one moment. I'm sorry for the technical things here. Okay. 13. Here we go. 13v to the 4th minus 54v squared. Oh, I'm sorry. I have to rewrite these in this order. 7v to the 5th plus 13v to the 4th minus 65v cubed. All right. Normally, I like to fill the time with dead air. Normally, I like to fill this dead air with distracting time, but focusing on my numbers. Okay, here we go. How many times does 7v go into 7v to the 5th? V to the 4th times. Multiply those, and I got 7v to the 5th. Multiply these, and I got negative v to the 4th. Subtract the result. Bye-bye. Hello. 13v squared plus minus the negative. Sorry, v to the 4th plus v to the 4th is 14v to the 4th. Bring these down. This is the part about this that I don't like. And one might argue that you shouldn't have to bring all those things down. You're right, you don't. Just the two terms right here. But eventually the others have to come down. And I am dividing this. 7v goes into 14v to the fourth 2v cubed times. And multiply those two, you get 14v to the fourth. And then negative 2v cubed. You know, sometimes people ask, if you know that this goes in this many times, then why are you checking to see what this thing is, see what it is? Because I'm trying to make sure that I did do it correctly, right, when I multiply. So I want to make sure that these do cancel the way they're supposed to, based on those lining up. Look, if those didn't line up, then you did something wrong, whether it was the math early or the math late. Anyway, add these here, subtract with the addition, and you get negative 63v cubed. 7v, I'm going to run out of room again. 7v goes to negative 63v squared, negative 9, v cubed, negative 9v squared times. I'm talking over my words a lot here tonight. Negative 63v cubed plus 9v squared right there. You know what? I didn't mind synthetic division on it. I'm just questioning if there were even more corners I could have cut. So my knowledge on that matter is not necessarily the boldest. My 11s, man. At least I made a good 11 there. 7v minus 1. 7v goes to negative 63v squared, negative 9v times. Okay. And that's negative 63v squared, of course. As I said, negative 1 times negative 9v is positive 9v. And those are bye-bye. And here we have subtraction, of course. That's negative 56v. These numbers should look familiar. We just did them in synthetic division. Excuse me, I need to write this. 7v goes into negative 56v, negative 8 times. 7v times negative 8 is negative 56v. Negative 1 times negative 8 is plus 8, and 11 minus 8 is 3. Okay, and then we should get that same answer there, the plus 3 over 7v minus 1. Okay, so these should be the same answers right here. Good, 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 good. Okay, so those are all good. Now, those aren't the answers, though. Those are the quotients. That's the result of dividing those two. The question, and I should have brought this up. I didn't read my own instructions. State if the given binomial is a factor of the given polynomial. Here's the binomial. They're asking, is it one of the factors of this polynomial? Well, within that question, what we're really asking ourselves is, was the remainder 0? Was the remainder 0? That answer was no. The remainder was not 0, therefore no, it is not a factor of it. And if you're wondering why the remainder has to be 0 for it to work, let me ask you using real numbers. Is 3 a factor of 24? I know you'll say yes, and you'd be correct. Is 6 a factor of 24? Is 12 a factor of 24? Yes, yes, yes. Is 10 a factor of 24? No. Why? Because you can't divide 24 by 10. Well, of course you can divide it by 10. You get 2.4. You get 12 over 5. But there's a remainder. There's a decimal, right? Factors are integers, at least for our real number world, are integers that can multiply together with no remainder. Same with polynomials in this case here. If I divide it and it gets no remainder, it is a factor of it. It doesn't have anything in excess when I write out the factorization. This had a remainder. It's had a remainder of 3 over the 7v minus 1, what have you. So if the remainder is 0, then it's a factor. If the remainder is not 0, then it's not a factor. So me writing this, I guess, was just a courtesy. All I was looking for was, I guess I erased my 3. All I was looking for was, oh, was this the 3? Did this exist? Was this non-zero? And as long as it was non-zero, then it was also not a factor. Okay. Yeah, that was a lot I stated, right? Let's keep moving forward and factor each completely. By the way, there are other ways that you can do that. You could plug in 1/7 into here and see if you get 0 out. I'm not doing all that right there. Wait, does that sound right? I think it does. Yeah. Factor each completely. Okay, now we're going to some factorization. And I don't know which order these things go. I know we're going to be solving some quadratics by factoring as well, so we're going to get into the quadratics. But this is a cubic. It's not a sum of 2 cubes. It doesn't have a common factor for all terms. Well, no, I take it back. It does have a common factor for all terms. It doesn't have an x as a common factor for all terms. But this does. Straight up, I see a common factor. I'd love to pull that thing out. I know for sure a 2. It looks like a 4 as well. So I can factor, I think at most, a 4 out of this thing. And I'll be left with 40x cubed minus 56. 56x squared plus 5x minus 7. Let me state a golden rule for those who haven't heard it from me. You always seek greatest common factors first. You always seek greatest common factors first. When it comes to factoring completely, you have to understand that even if you don't seek the greatest common factors first, number one, you're making the problem immensely more difficult for you, with a lot more options when it comes to factoring. The numbers are a lot bigger as well. Number two, you have to factor the common factor out anyway in the end, and you're less likely to do it once you felt like you've completed the bigger objective of factoring by grouping, which is what we're about to do. Once you feel like you factor by grouping, you're like, I'm good, I'm done with that answer there. You're not. There's a greatest common factor that exists, and it needs to pull out. In this case, it was a 4. And you know that 4 is the greatest common factor because when you look back in here, you ask, is there a greatest common factor still, other than 1, that you can pull out of all 4 terms together? Well, that answer is no. So the 4 is the greatest common factor here. I factored it out. It will remain factored out of here as I continue to, well, factor by grouping. And factoring by grouping means that you pair off consecutive terms, pairs of terms, like these two pairs and these two pairs, and you find the greatest common factor among those two pairs of terms. So with the 4 sticking outside of here, inside here, there's a greatest common factor among these two terms alone. Even if it's a 1, we're going to pull it out. In this case, it's more. Of 8, I think it's the largest, of 8x squared. And within there, there's still a 5x, and there's a negative 7. Now, within here, I'm going to seek the greatest common factor. In this case, you'd say there isn't one. It's 1. 1's the greatest common factor. And yes, factor it out. Plus 1. 1 factors out. And in here is left a 5x minus 7. Okay. You know, I've been doing this whole thing really playing under assumptions. I guess you haven't heard me teach some of this stuff before because we're only on problem number 9 and it's been 36 minutes. Okay, so the 4 remains outside. This is the part where some people get lost, but this is the part where I'm going to assume that you have heard it before or some version of it. See, if you did this correctly, and if this could be factored by grouping in this way, 5x minus 7 should be a common factor within these two larger terms, like within here and here. You can see that 5x minus 7 exists as a common factor within here. Therefore, we can factor the 5x minus 7 out of here, and we get 5x minus 7. And then what remains in those two terms that factored, that lost the 5x minus 7, is just 8x squared plus 1. So 8x squared plus 1 remains right there. And as long as this isn't a sum of 2 cubes, listen, if this was a cube right here, this would be a sum of 2 cubes. I'd keep going. There's no sum of 2 squares thing in existence right there. We're done. That's the final factorization. A lot of people tend to ask where the other 5x minus 7 go. It didn't go anywhere. I factored it out. Just like when I factored an 8x squared out of here. Where did the other one go? I factored it out of both. So that's the final factorization, and it is complete. The 4 stays outside. The 4 came outside. That is all a part of it. And we're good. You do check for other factorization that you have in here, though, when you're done. Okay, number 10. No apparent, I can't erase, no apparent common factor here that I know of. I'm questioning, I don't think that can divide by 3. So I don't think there's a common factor here, but you always seek greatest common factors first. I sought them, they're not there. But we will factor by grouping because we got pairs here within a cubic, and we will attempt to at the very least, and I'm sure it will work. Otherwise, there's nowhere that I know to go, assuming we haven't used the rational root theorem. So right here, I can factor out, I'm not struggling with this today, I think a 6 at largest with an x squared. And I'm left with a 3x minus 8. Now, as you saw before, last time 5x minus 7, 5x minus 7 appeared. If they aren't identical, then you can't factor it out properly. So, you know, you do have to make sure you find the greatest common factor, and if the leading term is a negative, you factor it out. If you don't factor it out, you won't get a matching positive inside the remaining quantity of what's factored. So factor out the negative at the very least, and at the very most, you're also getting out, it looks like, I think, a 7. And when I factor out a negative 7 there, I am left with a positive 3x and a minus 8. See how that works? You factor a negative out of there, this turns into a positive, this turns into a negative. And then this ends up being an identical common factor, which of course we can then factor out of that, 3x minus 8. And then here you also have 6x squared minus 7. And that is your end result of that. There's nothing else I can factor down further from that. Okay, there's some factoring by grouping for you. Now we have some other special case cubics here. In this case, potential difference of two cubes, sum of two cubes, things like that. Now, when you look at problem number 11, I don't see any perfect cubes. I don't know if you know your perfect cube values. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. See, we didn't hit 4. We got 5 cubed, 6 cubed, 7 cubed. I think 8 cubed is 512. 9 cubed, 10 cubed. Anyway, I'll stop there. I don't know the next one. Actually, I do. I know the next one. I don't know 12 cubed. Anyway, these aren't perfect cubes. So what do? Well, as always, you seek greatest common factors first. And, you know, a 4 can factor out of both of these. So I should factor a 4 out of both of these. And maybe we land in the right spot of 125x cubed minus 1. Oh, look at that. 125 is 5 cubed. 1 is 1 cubed. These are perfect cubes inside there. 4 factored out, and that led us to see that. Otherwise, we're stuck. We don't know what to do. We're just going to leave it like that. And for all intents and purposes, I guess it's possible that something can't be factorable, but this very much could. So this is going to be, you know, this is a difference of two cubes. And difference of two cubes states that a cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. So our first thing to do, potentially, in some problems, and I won't do this all the time, is to recognize exactly what these two things are perfect, what the cube roots of these are, you know, what perfect cube this represents. This represents 5x quantity cubed, and this represents 1 quantity cubed. This allows you to recognize what your actual a and your b are. So now, when we actually factor this part, the 4 is still on the outside. This becomes a minus b, 5x minus 1, times a squared, squaring 5x, that's 25x squared, plus ab plus 5x times 1, so plus 5x, plus 1 squared, which is just 1. And this is the final result on this thing. Pro tip, as long as you're only dealing with a quadratic in there, and you did any greatest common factor stuff you were supposed to before, this will never factor further. At least not with real number components. This will not factor further, provided you are just dealing with strictly a quadratic there. It's not some special, you know, quartic thing that can kind of do something else. This will not factor down farther. This is not a quadratic that can break down. Save you time by trying. Because you should be looking for other factors, but this one cannot. All right, 8x cubed plus 1. Let's see if you can deal out with this one. No common factor, of course, but there's a perfect cube in here in 2x. There's a perfect cube in here in 1. Now, the sum of two cubes is a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So the sum of two cubes here, this will give me 2x, because that's 2x cubed is 8x cubed, plus 1 times 2x quantity squared is 4x squared, minus 2x times 1, so minus 2x, plus that 1 squared is just 1. And you're done. Again, this quadratic cannot factor further. All right, number 13. This is a biquadratic. It's a special kind of quadratic in quartic clothing. Right here, you know, instead of saying like x squared plus 12x plus 32, it says x to the fourth and such. It's almost as if the x squared is being squared, and this x squared is to the first power, right? That's kind of what's going on. Now, there are a lot of teachers who will do different things with this. When I started off with my students, I said, if the perception of this x to the fourth and this x squared is daunting to you, you can use a temporary variable substitution, such as take another variable in its place. You don't want to put x in its place. I said it's like x squared, you know, blah, 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 blah. But you want to use a different variable to understand that we do need to bring it back to x and that we don't leave it in this temporary state. A lot of times in calculus, you start to use substitution with the letters u and v, and I'm going to do exactly that. I'm going to do u substitution here. I'm going to let u equal x squared so that, you know, when you look at the nature of x to the fourth being x squared, because this looks jarring as well, right? Instead, if I put a u here, u in place of x squared, it'll be u squared plus 12u plus 32. And although they're not x's, at the very least I see it as a quadratic, and I know when I factor this, it's some sort of u times this plus u times that. And now we are getting some sort of quadratic factorization. This is the next level of things that we're actually doing. So we are trying to find two numbers that multiply to make positive 32 and add to make 12. And in this case, I'm just going to, you know, save time somewhere. That's 8 and 4. Maybe if numbers get large enough and it's worth exploring as far as how we look for those factors, I'll do that. But as positive product, positive sum, not a massive number. It called to me when I found out what it was, and we're good to go. Now, this is the factorization involving u, but we need to put it back in as x squared. Thank you. Let's bring back x squared here, and this factors into x squared plus 8 times x squared plus 4. And, furthermore, because these are x squareds here, you do have to be careful and check and see if there's something that you can further factor. If this was x squared minus 4, for example, that would have been a difference of 2 squares, and I could factor that more, and I would have. That's exactly what I would have done. Now, I tend to not use u substitution, so if you want to do that, that's great. I'm offering that as a thing. What I do is I write the x squareds here as soon as possible so that I know I can just flat out ignore them. Once I recognize what's actually going on here in this biquadratic sense of going just even degrees descending down, I know straight away what kind of process we're in for here. Okay, so for example, right here, I know automatically I want to dive into some x squared thing and just say, okay, I need to find two numbers that multiply to make this and add to make this, provided, first of all, that there was no common factor going on right here. It doesn't look like that there is. So there's no, oh, by the way, this one's gonna be a little different because there's a 7 going on. But the point is, I know that x squareds are going to exist there. So if you don't mind, without u substitution, I'm just going straight in and do that. But I do know it's x squared and x squared. Now there's one other thing here now that we're factoring a little more deeply, and I use mental guess and check factorization. We know that 7x to the fourth comes from 7x squared times x squared. And I almost want to use u now because this is our first factoring. That's a larger, that's a larger quadratic. That's a value that's greater than 1 that we couldn't fully factor out. But I don't know if we treat them like x's. We know that 7 times 1 gives us 7, and that's the only thing we can do, right? Because it's a prime number. Now, 36 has a multitude of possibilities right here. 36 could have been 36 times 1. By the way, I don't know the answer right now. I'm sure I'm going to mentally come up with it as I keep writing this out. But 36 times 1, 18 times 2, 6 times 3. Oh, I'm sorry. Not 6 times 3. 6 times... I don't know why I said... Oh, because I was thinking of 18. 12 times 3. 9 times 4. And 6 times 6. There are a bunch of possibilities here that can multiply to make 36. We have to find the right combination that gets placed into here so that when we do the foiling, that we know that 7 times this number plus this number, 1 times this number will give us negative 59. Now, that being said, we also have to know that negative 36, being a negative product, means that one of these is positive, one of these is negative. I do not yet know that this is the plus and this is the minus. This could very much be the minus here, and this could be the plus. I don't know. But what I do know is that if I put a plus and minus here, it leaves out imagination. So I know tangibly what it is that I'm doing with one sign and the other. And if I get a positive 59 as the result, I know that all I have to do is switch these signs here. And I almost hope that I get that so I can show it to you as validation that that works. Again, this is assuming you haven't done one of these with me before. Now, there are some other kind of little clues that you can do to assist you here. Some small ones to help alleviate a little bit of the pain. Not too much. It looks like we're going to have to do a few tests here. But 59, being an odd number, has to come from an even number plus an odd number. And you get an even plus an odd if, when you multiply some things that you, given that 7 and 1 are odd numbers themselves, one of these has to be an even, one of these has to be an odd. If both are odd, you're going to get an odd plus odd scenario, which gives even numbers. If you get both evens, you have an even plus even scenario, which are both evens. That means we can't possibly be looking at 18 and 2 as our possibilities, or 6 and 6, because those are just even numbers. That'll leave me with an even plus an even that gets me an even. So the possibilities lend to these ones as well. Now, other things I would consider looking for and being aware of is, are any of these factors of 7? Because if they were factors of 7, that means I couldn't place them in here. Because if I did, let's say 14 went in here. Well, hey, I could factor a 7 out of here and I have x squared plus 2. Well, we shouldn't be able to factor a 7 out of here because this didn't have a common factor of 7. So no common factors of 7 should exist in here. Unfortunately, honestly, because I wish there were factors of 7, because then I knew what to eliminate, unfortunately, none of these are factors of 7. By the way, I won't go this slowly for the other factoring problems, I promise. This is my first time kind of doing some of it with some people who might not have really felt out the first time what my strategies are. So now we try and pick in some numbers. This can either be, right, 36 and 1, 1 and 36. This could be 12 and 3, 3 and 12. This could be 9 and 4, 4 and 9. There are up to 6 possibilities that we may potentially try. Now, I'm going to try and alleviate it given the size of 59. Not that it's massive or not that it's tiny. Given the size of 59, I know that there's no chance in hell, pardon my language, there's no chance that this is going to be a 36 here. Because what's going to happen? You have to do 7 times 36. You know what that is? Big. Much, much bigger than 59. And, sorry, adding 1 to that number to trying to bring it back is not going to bring it back. That's going to be way too big. I'm not going to bother calculating it. I don't care about what that is. You can try 36 here, but you know what? This isn't big enough. 1 times 36 and then subtracting with that other one, that's not going to get us to negative 59 or positive 59. So this one's out. I know it's out, right? There's a logic in understanding some of your numbers that are going to help you. I don't think 12 and 3 are going to work either. Listen, I haven't done these problems before. I don't think 12 and 3 are going to work. 7 times 3, 21. But 12, no, too small. 12 right here, a little too big. 84, too big. Ignore them. Done. When I say I got these things to test, I don't ever actually really test them. Me writing this down is a courtesy for you. I don't actually ever test them. I'm telling you they don't work. 9 and 4, I'm seeing where these need to go. I'm seeing where these need to go. Is it this one? No, too small again. Negative 28 plus, no. This one here, 9, 4. Negative 63 plus 4. And I say 4 because this is 1 times 4. Negative 63 plus 4 will give us the negative 59 that we're looking for. And guess what? It is a negative 59 there. And this ends up being the factorization. Ultimately, when I go through my numbers, there are things that it depends on your mental ability and what you can do with numbers. This is why you always want to practice number sense here. But I truly only actually tested one number. I considered the 12 and 7 times 12. I mean, no, I considered it, but it wasn't going to be it. I would have considered the 6s and things if for a moment because reasons. But that would have given me an even result, and I know 59 is an odd number. So anyway, so this is what this one becomes right here when it comes to factoring that, and we'd be done with that portion of that factoring. But then you don't want to box this yet. You're not done because, hey, I have an x squared minus 9. That's a difference of 2 squares. X squared minus 9 is x plus 3 times x minus 3, right? That's that difference of 2 squares knowledge that you need. You're an integrated math 3, you need to know that now, right? So that's the a squared minus b squared thing going on there. And that's the full and final factorization of this. So I know I spent a long time on that problem number 14, and I promise I won't spend as long on those ones, but I'm going to go through the same iterations and the same ideas as far as what you need to do, what kind of strategies you can employ, and, flipping numbers, what are common factors, this and that, because that will make us faster. I don't know how much factoring is involved. Obviously, integrated math 3 is less about the quadratics, right? But that's a strategy where, for my final, about 2 hours to do 40 questions. That's averaging 3 problems a minute. You want to be able to do this problem, in 3 minutes. I mean, obviously I didn't, but you want that idea going on. Okay, here we go. Number 15, find all zeros. What are zeros? Well, zeros are x-intercepts. X-intercepts. They are values of x in an equation when y equals 0. So you are doing that right there. Now, there are other words that they can use interchangeably with this. They might say solutions. They might say roots. There are different words here where I don't know if always with solutions. I believe with solutions they can just use a y right here and you got to plug in 0. I'm pretty certain. Otherwise, if they just final solution, solve it when it's equal to 0 here. But we're setting this equal to 0. X-intercepts are values of x and y equals 0. The zeros are the zeros for y. What are the x's in those cases? Well, we do have this factored, and I have to write it this way. This is an OCD thing for me. We do have this factored form right here. Now, some natural inclination will be, FOIL, distribute this thing back out. No, don't do that. You are actually in good shape. You are more than halfway there having this factored. You have a product. A product set equal to 0 is nice. You get to use what's called the zero product property. If a times b equals 0, then a equals 0 or b equals 0. What did I just say right there? What I just said there is if you multiply two numbers, well, it doesn't matter if it's 2 or 3 or 7 or whatever numbers. If you multiply things together and your result is 0, number one of them has to be 0, meaning it's impossible to multiply two non-zero numbers to get 0. Number 2, as long as one of them is 0, the result is 0. Think about it. 0 times a billion is still 0, right? So the idea is we're trying to find what value or values here of x would make this whole result 0. If 5x minus 1, if this quantity was 0, 0 times this would give us 0. So what is the x value that would make this true? I'm low on room, so I'm going to add 1 and divide by 5. I get 1/5. Please leave the answer as a fraction. Improper is even good. And if x minus 5 equals 0, add 5 to both sides, x would equal 5. See, if I substitute 5 for x in here, 5 minus 5, 0. Doesn't matter that this number's 24, So those are our two answers there. Either x can equal 1/5 or 5. And we're solved. So our goal for these things when we find the zeros is assuming they're factorable. And that may be a heavy assumption, but you know what? We're only playing factoring here, no completing the square quadratic formula. Assuming they're factorable here, we want to set this thing equal to 0, we want to factor it, and we want to solve using the zero product property. So I'm about to set 3x squared plus 11x minus 4 here equal to 0. And I'm going to factor this guy right here in the same way I did last time. 3x squared is some form of x times x. Now, 3 can only come from 3x times 1. That's a gimme. 11 is an odd number. I need to choose factors of 4 that are not 2 and 2. If I choose 2 and 2 here, I'm going to get an even plus an even. And I can't get an even as a result. This has to be some form of 4 times 1. I'm going to put plus and minus here because the negative product here. And it's either 4 and 1 or 1 and 4. And either's valid. If you try 4 and 1, you might realize it's too small. Negative 3 plus 4 is 1. Let's try 1 and 4. This is negative 12 plus 1, which is negative 11. We want positive 11. Did we make a mistake? Not really. We're in the right spot. We have the numbers in the right positions. We have to switch this plus to a minus and this minus to a plus. But at least we had that tangibilization. We had that idea of what we needed and how we could calculate. It's really helpful to write that, erase it, change it. We're good. This is 12 minus 1. That's our 11. See, we know 3x times x is 3x squared. We know negative 1 times 4 is negative 4. We're trying to figure out the outside and inside part ultimately. That's why we choose those numbers. And we're good. Okay. So, anyway, if 3x minus 1 equals 0, see if you can do this with me mentally. If 3x minus 1 equals 0, you add 1 to both sides, you get 3x equals 1. You divide both sides by 3, you get x equals 1/3. And if x plus 4 equals 0, subtract 4 from both sides, x equals negative 4. This is one of those where you just switch the sign kind of thing, and you probably want to get used to that. That happens in a lot of scenarios. When we graph polynomials at the very end, you're going to probably see me do a lot of sign switching like that. All right, let's continue solving by factoring. And naturally, we have the harder ones first before the easier ones, because these ones are already factored. I would probably do these ones first, but I'll just stay in order. All right, let's solve by factoring right here. Now, in order to solve by factoring, again, zero product property. That's the end goal, which means set it equal to 0. Not just set y equal to 0, set the equation equal to 0. I have a 70k squared right here. I'm going to go ahead and leave it right there. I have a negative 145k on this side. Let's add it over. I have a 75 over here. Let's subtract it over. Okay. Oh, shoot. Never mind. These divide by 5. I was going to say, I want to divide these by 7. 75 doesn't divide by 7. These are all divisible at the very least, I think at the very most, by 5. Factor the 5 out. There's one more thing I'm going to do with this 5 ultimately, and I'll show you what that is. So this is 35k squared plus 29k minus, I know this, 15 equals 0. Now, there are one of three things you can do. Two are mathematical. One is you could say, because 5 is now a common factor, divide both sides by 5. And 0 divided by 5 is 0, and it's gone, which is totally valid and something that most people will do. Some people might say divided by 5 from the beginning. I just want to warn you on that, though, because, you know, when I factor out, say, this 4 right here, I'm not dividing these by 4. The 4 didn't go away. I have an equivalent expression here to start with. So some people might argue that practice with your common factor things, especially when I hit the rationals. Practice with common factors and then find something that divides. So one way, divide both sides by 5. Second way is this. It seems a little weird. Zero product property. If this times this equals 0, either 5 equals 0, which is impossible, or 35k squared plus 29k minus 15 equals 0, which is what we're looking at. This is equivalent to dividing both sides by 5. The third thing is just ignore the 5. And that's not really mathematical. There's a mathematical basis to it. Never, if a variable is a common factor, you can't divide that variable out. That's actually considered as a part of your zero product property, which is the reason why I said this other one right here. So anyway, our goal is to now factor 35k squared plus 29k minus 15. Let's, good luck. I don't know. I don't know if that's factorable from the onset, so I'll play with it for a moment. I might even pause this for a moment because I got to think in terms of what I want to say on this. When I'm looking at that, I don't think it's factorable. Let me make sure I even did any math right here with dividing here. Just give me 1 second. Okay, I literally paused for 1 second before I realized the dumbest mistake of all time. 70 divided by 5 isn't 35. Apologies to everybody for that. 70 divided by 35 is 14. Okay, so 70 divided by 5, excuse me, is 14. It's been a very, very long day for me. All right, anyway, so apologies for that. I caught on once these were all odd numbers. That wasn't possible to factor. So I don't know if this is possible. I assume this is possible to factor, and at least there's a possibility of it being possible to factor. All right, so here we go. Let's start working on this one here. Now, 14 is a composite number. 14 comes from either 14 times 1, 14 times 1, or 7 times 2. And 15 comes from either 15 times 1 or 5 times 3. So there are a few possibilities to dive in here. And, the even-odd argument doesn't really work here because 14 has an odd and even factor no matter what. And none of these are common factors with each other. So this is one of those instances where you may be testing a few more times than you wish you did. One thing that I would definitely look to is understanding that, once again, with a negative product here, though, having a plus and minus right here, that you are going to have to, go back to 29? Meaning when you add your two numbers, a positive and a negative, see, I might have to do something like 40 minus 11. I won't do something like 20 plus 9. They're not going to be the same sign. So I got to make sure that when I multiply two numbers, one of them's got to be more than 29 when I multiply those two numbers. That's the one only strategy that I can for sure do with you as I test numbers. And then just press your luck. I don't know. Sometimes I test the ones that are like closer to each other, that are closer as far as factors, just because I felt like if it were these numbers, they'll either get too big or too small. Like I'm not going to do 14 times 15. That'll be too big, and 14 times 1 isn't big enough. So I'd rather work on some of the other numbers here, like 7k and 2k, alongside, say, like 5 and 3, like that. Now that's negative 21 plus 10. That doesn't get us there. So maybe swap the 5 and 3 and try that. And you get negative 35 plus 6. That's negative 29. That works. I need a positive 29, but just switch the signs. So you see, there is still number sense, even though it's kind of a guess and check. It's almost like press your luck before you swap everything. And I'll have you know, I don't tend to write down those numbers. I picture them in my head, and I'm doing this stuff, and it's just a little bit of erasing for it to work. But yeah, ultimately you do get to the factorization. 35 minus 6. You do get there. All right, we still got to solve this thing, right? So we have a very poor looking k. Either 7k minus 3 equals 0, add 3, divide by 7, k equals 3/7. Or 2k plus 5 equals 0, subtract 5, divide by 2, k equals negative 2/5. I mean, outside of my poor division by 5 there, and obviously talking through it with you, you tell me a faster way you would do that. Go ahead, tell me. Hopefully you can divide better than I can. YouTube used to be able to let us do annotations where I could put up like a little thing right there that just says, mistake, I'm going to correct it, whatever else, while other people are watching this going, what is this nut doing right here, right in this problem? All right, let's keep going here. Number 18. Number 18, 10x squared plus 28x equals negative 16. I'm going to go ahead and add the 16 here to both sides. And I get, plus 16 equals 0. These do have a common factor. If I factor out and divide by that number, can you entrust me in the idea that I factored it out first before I divided? I'm going to divide everything here by 2, and I get a 5x squared plus 14x plus 8 equals 0. Make sure I did all the division correctly. Make sure there are no greater common factors. Okay, now this one's nice because everything here is a plus and 5 is a prime number. So 5x times x and plus and plus. That's really nice for us. Now 8. Listen, I'm gonna go fast. But 8 being either 8 times 1 or 4 times 2, and 14 being an even number with odd factors here, we got to use some version of 4 times 2. 8 and 1 would only lead us with an odd linear coefficient. So it's either 4 and 2 or 2 and 4. Which one would get us to 14? If I put a 4 here, it'd be too big. So let's try 2. 10 plus 4, 14. There it is. Okay, so you can see how it can go fast based on good strategy there. If 5x plus 4 equals 0, x equals negative 4/5. Don't take my word for it. Try it for yourself. If x plus 2 equals 0, x equals negative 2. When they say solve by factoring, we got to assume those are factorable anyway. By the way, if you tried, just speaking of which, if you tried everything and your math was good and nothing worked, like if that thing was 35, nothing would have worked, then it's not factorable. But if they're asking you to solve by factoring, you better hope it's factorable, especially if on a multiple choice final, it's not factorable option. All right, number 19, this one's already factored here. Straight up, either 6 equals 0, which is impossible. You could ignore that. You could divide both sides by 6. Either 6 equals 0, or x plus 3 equals 0, so x is negative 3, or x minus 8 equals 0, so x equals 8. I don't really have anything else to say on the problem there. And honestly, same with number 20. These are the ones where I can go a lot faster. Either r equals negative 3 or r equals 8. You just got to be careful. You just got to be careful and make sure that this side equals 0. You've got to make sure this side equals 0. If this had 10, this isn't a thing. Not even, obviously, r wouldn't equal negative 3, but r plus 3 wouldn't equal 10 either. There's no 10 product property. That's not a thing. And if this did equal 10, you'd have to set this equal to 0. You'd have to distribute this whole thing out. That would have been a good problem. You'd have to distribute this whole thing out, subtract the 10 over, combine like terms, factor again, and then go ahead and solve for that thing. That's a lot to do. But there are problems like that, right? 0 is very special for the 2 reasons I stated before. Number 1, no 2 non-zero numbers can multiply to be 0. One of them has to be 0. And number 2, as long as one of them is 0, then the whole result is 0. Both don't need to be 0, right? That's not true for something like 10. Okay, we're done with the factoring stuff there, and really done with, I think, the big bulk of the quadratics, which to me is kind of unfortunate, because I like to preach, no, I take it back. When we do our rational stuff, I'm sure we're doing a lot more factoring, and I'm going to go a lot faster on those for other strategical reasons. All right, evaluate each function. W of x equals 4x plus 3, find w of 2x. What they're really stating here is that x is not just a variable, it is our input, and our input is right here. Now they're asking 2x to be your input. So when they say find w of 2x, they're saying wherever an x exists in your expression for your function, substitute the new input for it. Like I joke in my class, if this said find w of booger, this would be booger right here. So a 2x is going in the place of x here. This will be 4 times 2x plus 3. This is actually a pretty basic problem. 4 times 2x is 8x, and you get 8x plus 3. And that is w of 2x. That's it. I'm done. Number 22. Now we have 2 different functions. G of x equals x squared plus 5, and f of x equals 2x plus 2. We are going to find g of f of x. This is known as a composition of functions. Sometimes you'll see the notation like this, g of f of x, like that. That's not an O, and it's not a dot either. It's a little open circle. I don't know what it's called, but you'll sometimes see the notation like that as well. All right, what are they asking you to do? When they're asking for g of f of x, I'm gonna make it a little bigger so you can see it. G of f of x like that. I want to make sure that you know it's not like g times f and whatever like that. F of x has an expression. It's called 2x plus 2, and I'm going to take g of 2x plus 2. And you just saw in the previous problem what I did with this thing. The input is going to replace x anywhere in this function. G of x is x squared plus 5. G of 2x plus 2 is 2x plus 2 squared plus 5. Wherever there's an x in this expression, I'm replacing it with the new input. And that's what we're doing. So now what I'm going to do here is, they want us to simplify this thing, especially when it comes to finding inverses. There are a bunch of different ways to do that. So this is a perfect square trinomial. I square the first term, double the product of these two terms here. 2x times 2 is 4x, doubled is 8x, and square the last term right there. That is my perfect square trinomial. I told you I'd be faster with them, and that's it. Now, combine like terms, you get 4x squared plus 8x plus 9, and that is the result of g of f of x. All right. And now there are other things we're going to be doing with composition of functions when we have to find an inverse. when you're testing to see if two things are inverses, you would compose one function with the other, and if it simplified to just equals x, then you actually have inverses of each other. So we'll see. This was just composing them. It wasn't asking if they were inverses. I don't think there was any rhyme or reason for that. Okay, number 23. We're not even halfway through number-wise, so this is me doing a lot of teaching. Who knows? Maybe this will be just as long as my 150 question one. Now we're going to find f of g of 3. There are two different ways you can do this. You can either, and I don't know if the first one's necessarily recommended. It depends on what you're doing plugging in numbers. You can either find f of g of x first, which I am going to go ahead and do so you see a little more practice with it. You either find, actually this is going to be no problem at all. This is a very short problem. You can either find f of g of x, which means take g of x's expression, x minus 4, and place it in for this f right here, 3 times x minus 4, or place it in for x, which is 3x minus 12. So this is f of g of x, right? And then you substitute 3 into here. So f of g of 3 would be 3 times 3 minus 12, which is 9 minus 12, which is negative 3. All right, so that's that answer. Or you can substitute, which is more often recommended. It depends on how big the expressions are for the functions. Or you can take g of 3 immediately, which this, I think people might like this version more also because what it represents, you work from the inside out. Take g of 3 immediately, which is 3 minus 4, which is negative 1. And then you're taking f of that negative 1 because g of 3 is negative 1. So you're doing 3 times negative 1, which is negative 3. See how people might appreciate that more? And that's really what you're doing, actually. You're taking f of whatever g of 3 is, the value of y in this function when x equals 3. And that's what you're composing. And that also kind of explains why inverses work the way that they do. The y of your inverse gets you back to your x. That's why those things are inverses of each other. I won't explain it when we do it, and I think we're going to run across it very soon. Where the, hey, here they are. So state whether they are inverses or not. All right, I have two things here, h of n and f of n. Unfortunately, I'm not going to be very quick on this problem because I promised my students I would show 4 different ways to do this. You only have to do one. You only have to do one. But I'm going to show you 4 different ways to do this. Since I just came off compositions, I'm going to do this first. The first way that you can do this is, now these are n's, not x's, so pardon me when I use n's instead of x's. The first way you can determine this, and I'm going to erase this later, is you compose one function with another, like h of f of n, and you simplify it. And if the end result is n, you have inverses. That would mean that h of n is the inverse of f. Or the other way around. The other thing you can do is compose f of h of n, like that. And if you get n, the same thing, that means that f of n is the inverse of h. Whichever way you want to write it. They're inverses one way or the other. The third thing you can do is actually take the inverse of h of n and see if you get this exact expression. You have to simplify, you have to make it match appearance as well, so you have to be careful with that. And same thing with this one. You can take this inverse as well and see if you get this match. And of course, again, it has to match. Like, for example, they put a common denominator of 4 joined as a single fraction here, and they put the common denominator of 7 split. Why? I don't know. But those are, you have to make them match in terms of appearance, or you have to, like, don't force the match, for example. Like, if it's not the right number, if it's not equivalent, don't do it. But, don't get an answer, for example, 16 over 4 is 4, right? So don't write 4 plus 7n over 4 and go, when you take this inverse and go, oh, look, that's not the same as, like, oh, these are not the same thing. Guess they're not inverses. No, 4 is 16 over 4. So I'm going to be careful with that as well. But I'm not starting with that. I'm going to start with the composition of functions. And I'm going to start with h of f of n. And this might be a little, tricky when it comes to all the fraction biz. So be careful here. So h of f of n means h of 16 plus 7n all divided by 4. This is going to take n's place in this expression. I know people don't like fractions, but here we go. So, and honestly, I hope the answer is yes to like them being inverses because it validates a little more of what we're doing. I have no idea if it's going to or not. I'm kind of suspicious of it actually. So what we're going to do is we're going to take 5/7 of 16 plus 7n divided by 4. And we are going to be subtracting 18/7. Now, right here, when you multiply fractions, numerator goes with numerator, and then denominator with denominator here. So honestly, what I can do here is I can distribute the 5 into these two, right? We have to distribute this thing. We have to simplify this thing. So 5 times 16 is 80. 5 times 7n is 35n, and this is divided by 28. Now, I don't think so. Now, 18 over 7 needs to have a common denominator. I'm going to multiply top and bottom with 4 as 4 over 4 here. So we can then subtract this thing, and we get negative 72 over 28, I believe. So when I subtract these here, I ultimately get, now it's a common denominator. This is like all over 28, right? So 8 minus 72 is 8. And there's a 35n here. So I'm left with 35n plus 8 all over 28 simplified. Bottom line, this didn't just break down to equal n. Very sadly, this didn't just break down to equal n. That means if h of f of n is not n, these are not inverses. Are these inverses? No. And very sadly, I'm going to spend time doing the other 4 versions, or the other 3 versions of the 4, to show that they're just not going to be inverses. That's not very rewarding and gratifying. But you know what? It's within the test, and you choose what you choose to test. So I want to show you all 4 of these. And, you know, you're looking at this and saying, why would anyone want to do this way? Well, not everything's fractions like this, right? Sometimes these are faster or easier to do than the other ones. Sometimes. And it's also just good to show how compositions of functions really work things out. All right, let's go ahead and let's do f of h of n. So this time, that means I'm going to be doing f of 5/7 n minus 18/7, which means this will take place of n in the fraction. So that will become 16 plus 7. Ooh, there's good news at least right here. 7 times 5/7 n minus 18/7. At least 7 times these things means it just gets rid of the fraction. That's good news right there. And this is all divided by 4. Anyway, this equals 16 plus. And yes, as 7 distributes into these things here, effectively 7 over 7 is 1, 7 over 7 is 1 there. So you're going to be left with plus 5n minus 18 there, because the 7 already took care of the distribution, all over 4. And this 16 minus 18 is negative 2, so 5n minus 2 over 4. And that thing doesn't just become n. There's nothing else I can really clean up to just make that n. Other things would cancel, you know, outright, and things would happen. So make sure that's all good. It is. Okay, so once again, no. No, that doesn't equal n. I'll just say which doesn't equal n in case you're looking at this at, like, you're fast forwarding to it. That doesn't equal n, that doesn't equal n. That kind of looks weird. All right, last 2 versions I'm going to do is, and this is a little weird because these aren't actually the letters x and like y, and like these don't need to be y because they're a function notation. But what you generally do, let's say that it was like y equals, you know, 2x plus 3. I'm going to do a very basic one first, and I'll go to it. To find the inverse, what you do is you swap your independent and dependent variables, and that would be the inverse portion. So when I'm taking the inverse, what I would do is I would swap x and y, like that. And then I would end up solving for y, because I want to write the kind of function notation version equivalent. I want to see if it's going to match what the other one was as a function. So I would isolate y, I would subtract 3, I would divide both sides by 2. So swapping x and y do that. Now, I don't have the letters x and y here. I have the letter n, and then I can use y still, right? Y can represent h of n, f of n. That's fine. So what I'm going to do is I'm going to take h of n's equation. H of n equals 5/7 n minus 18/7. And I don't like to use h of n itself in the equation, because it's weird. I'm going to place y. I'm going to put y in its place, if you don't mind here. And what I'm going to do is swap. I was going to say x and y. I'm going to swap n and y when it comes to taking the inverse. Once you swap it, you have taken the inverse. But I need to isolate that y in order to confirm that it doesn't match what this one becomes here. So to get y by itself here, honestly, I want to bust the fraction right now. I'm going to multiply everything by 7 right now. Not a fan of fractions. As soon as I can get rid of them, let's do it. Multiply both sides by 7 here. I'll get 7n equals 5y minus 18. Even though, listen, I'm going to have a fraction in the end here. I'm going to add 18 to both sides. I'm going to write 5y on this side, though. 7n plus 18. And then we're going to divide both sides by 5, and you get y equals 7n plus 18 all over 5. Now, one version of this that you want to consider writing is like, oh, for example, see how they have the 7n on the right side? Maybe let's put the 7n on the right side. How they're all divided by the same number? Let's make sure ours is also all divided by the same number, which it is. Again, you need to see if it matches in this case. Now, that is our version of the inverse of h. So inverse of h is 18 plus 7n all over 5. The inverse of h does not equal f of n. F of n being 16 plus 7n all over 4. They're close in as far as like what they can do appearance-wise, but they're not the same. So once again, no. So again, you choose which method. Honestly, arguably, this was more steps than these ones. Actually, I liked this one the most so far. The last one, actually this isn't bad. The last one, let's take f of n. Looks like I need the room. So f of n as 16 plus 7n divided by 4. I'm going to call this y for mathematically convenient purposes. I'm going to swap n and y here in the inverse step. And I'm going to get n equals 16 plus 7y, all divided by 4, and let's solve for y. First step here will be just like last time. Bust that fraction. Multiply both sides by 4 right there. I got 4n equals 16 plus 7y. I subtract 16 from both sides. I get 7y equals 4n minus 16. And I divide both sides by 7. I get y equals... remember when they did both these divided by 7 like separately? I'm going to go ahead and do that separately. 4 sevenths n minus 16 sevenths. Again, your goal is to attempt to give the matching appearance. So I'm trying that. And of course, they're not the same. They're similar looking, but not quite the same. The inverse of f equaling 4 sevenths n minus 16 sevenths means, as this was 5 sevenths n minus 18 sevenths, that the inverse of f does indeed not match h of n. So lastly, no. The answer is these are not inverses of each other. So I did a lot of work with those things when it came to determining whether or not they were. You only choose one of these 4. Those are essentially your 4 options. A fifth option would be graphing these two and see if they reflect across the line y equals x. I think we do get to graph something with its inverse as well. And then when we do that, we'll see what that means as far as that. But we didn't have a graph for that one. All right, number 25, find the inverse of each function. There's only one function we're taking to find the inverse of. So f of n equals 8 minus 9n over 2. This is just me, that one-step thing, or not one step, just one version of what I'm going to do here to find the inverse. I'm going to turn this thing into y. Why don't they do f of x's? Come on now. 8 minus 9n over 2. Let's go ahead and now take that inverse by swapping n and y, 8 minus 9y, all over 2. Multiply both sides by 2. And you'll get 2n, all this space, you'll get 2n equals 8 minus 9y. I'm going to add 9y to both sides here. I like that being positive because I don't want to divide by a negative, have a negative in the denominator. That's not a good way to go. So I'm going to add 9y over here. I'm going to subtract 2n over here. 8 minus 2n, negative 2n plus 8, whichever one. And divide both sides by 9, and I'll get y equals 8 ninths minus 2 ninths n, or, of course, 8 minus 2n all over 9. Either or there, whichever one. Do you guys prefer this? I'm going to write it this way because this was that way. It's kind of nice to get that cohesiveness. One looks like it. The only reason, one of the reasons I'd want to put it this way, and actually I'd put the n term first, is because if I want to graph it and put it in slope-intercept form. And I think that would be a good reason to do that. But I guess not this time. So the inverse of this guy is 8 minus 2n over 9. Check that out. 8 minus 9n over 2 and 8 minus 2n over 9. Hey, they're inverses. If I didn't mess up, they're inverses. I want to make sure I didn't. I don't think I did. No, I'm good. Okay. Find the inverse of each function. Just probably one of these. Then graph. Okay, here's the one. Then graph the function and its inverse. So now I have h of x equals x minus 1 quantity cubed. I'm going to go ahead and graph this one first right now. So I'll go and graph h of x. I'm going to give it this color. And x minus 1 quantity cubed. So what this means here is, as far as equations go, and y equals a times x minus h quantity cubed plus k. Your center, your reference point that we start at here is at h comma k. It's kind of that middle where we have that rotational symmetry, right? And then a represents your vertical stretch factor. Your vertical stretch factor, which means whatever this value, it's a 1 in this case, whatever this value is after you cube your values, you multiply by that amount to stretch it more, or if it's a fraction, you might shrink it, or if it's negative, you might flip it. Anyway, we're going to start at our hk value. Now, if we were to write this in kind of a more raw form, this would be a 1 times x minus 1 quantity cubed plus 0. That means this center point that we're going to start at is at 1 comma 0. Remember, you flip that sign, minus h. The h is 1. Sorry. I was going to say something else about plugging in 1 into here, which is what you do. 1 comma 0. So I'm going to start at this point right here, at least for this part of this graph. Now, this is a cubic function. It'll behave like a cubic function. That means as I displace myself some number of units in the x direction from here, you go up that amount cubed. And it's times 1. That means you just go up that amount cubed. When I go over 1, I go up 1 cubed, which is 1. When I go over 2, I go up 2 cubed, which is 8. Now, unfortunately, Unfortunately, 8 is off the graph. However, that never stopped me from pretending. When I go 2 over, I'm going up 8. So 6, 7, 8. Why not? I want to get that general nature. I like that idea. And I'm going to do the same thing on the other side here. Negative 1 cubed is negative 1, and negative 2 cubed is negative 8. Negative 6, negative 7, negative 8. 8 down from your center, of course. That's what I'm referring to there. And there is the cubic graph for the first guy right here. So let's go ahead and get that thing going through, like that there. And out the other side right there. Now, for my students in their final, keep in mind, even though there's multiple choice sections in the final, you're mostly asked to graph. The free response stuff will be often graph based. Kind of be ready for that. Sorry, my camera's kind of moving on its own here. All right. We still need to find the inverse. We still need to graph the inverse, and I'll tell you about how you could actually graph this thing without even actually calculating its inverse, but how we can also practice graphing cube roots at the same time. So I am going to find the inverse first, then I'll say what the whole graph thing means as far as symmetry goes. Let's go ahead and let's find the inverse of h by turning h of x into y. Let's swap x and y for the inverse step. And let's solve for y. Now y is being subtracted by 1 and all being cubed. It is the princess in the proverbial castle. We need to get it out of the castle first by slaying the dragon that is the cubic. Let's take the cube root of both sides, and I can do that right now because the cube is isolated on this side. Cancels out the cube, and you're left with the cube root of x equals y minus 1. If I add y to both sides, if I add 1 to both sides, I'm going to write y on this side though, but if I add 1 to both sides, I'll get y equals the cube root of x and then plus 1 on the outside of that. So y equals the cube root of x plus 1, or the inverse of h equals the cube root of x plus 1. So here is your final result for the inverse. And we are going to go ahead and graph this inverse. We're going to graph this cube root. Now cube roots are graphed in the same kind of vein as far as a times the cube root of x minus h plus k. This is assuming there's no horizontal stretches that we're talking about here, of course. Now, in this case here, we're referring to a center, because there's no kind of h in there, that x is 0, and then the k value is 1, so the center's at 0, 1. This will be in green, of course. Now, cube roots do literally the inverse of what cubics do. Before, we would be going over 1 up 1 over 2 up 8. Now we go up 1 over 1 up 2 over 8. Or the way that I put it is let the cube root do its work. If I go over 1, I'm going to go up the cube root of 1. The cube root of 1 is 1. If I go over 2, I'd go up the cube root of 2. That's not a perfect cube, right? 2 is not a perfect cube. Neither is 3 or 4 or 5 or 6 or 7. But 8 is. So if I go over 8, then I'll go up the cube root of 8. So if I go over 8, 6, 7, 8, the cube root of 8 is 2, and that's where I go up that 2. That's kind of how I do it. You can do that opposite of 1, 1, 2, 8. That's fine. Now negatives, you can take the cube root of a negative number. Unlike square roots, you can take the cube root of a negative number. Cube root of negative 1 is negative 1. And the cube root of negative 8, that's the next perfect cube I can do, is negative 2. And we're right there. And I'm going to go ahead and do the best I can with this giraffe. Obviously, I did not give my best effort in that one fell swoop. It's really hard to go this direction. I do want this to actually look relatively decent because the nature of how inverses work with their functions. I apologize, it's this tablet thing that I got to work with. I'm going to have to... Oh, I'm better drawing that way. There we go. I'm going to have to deal with what that looks like there. Okay, let's try this side here. Yeesh. Will you accept this drawing? Okay. All right. Okay. We drew the function and its inverse. I'm going to blacken these out for a moment, and I want to show you something because you got to draw this probably in pencil. Check this out. Do you notice... I'm trying to get that in black. That's okay. Do you notice when you tilt your head, I have to tilt my head this way for you to see it that way. Do you notice something about these lines here? That Rorschach ink blot symmetry across this line y equals x. Do you see that symmetry that there is here? That if I reflected one curve above across this line here, you make the other curve out from that. Isn't that cool? That's what inverses do. Inverses have a reflection across, literally across the line y equals x. And isn't it interesting that, you know, it's called the line y equals x such that x equals y, or x takes y's place and y takes x's place. You know how I could have graphed the cube root function without getting the cube root function? There's a point on this graph here that is 1, 0. There's a point on this graph here that's 0, 1. 1, 0, 0, 1. See the flip-flop? There's a point on this graph here that is 0, negative 1. There's a point on this graph that's negative 1, 0. 0, negative 1, negative 1, 0. X and y flips. This is true for all those points here. 2, 1, 1, 2. 8, I think this was 8, right? 8, 3, 3, 8. Negative 1, negative 8, negative 8, negative 1. So I could have found out what these points were, swapped the x and y, and graphed it that way. Even if you don't know how to graph this cubic, or this cube root, right? You might not know a lick on how to graph the cube root and just reflect it across y equals x. Just reflect it right across that line right there and say, this is going over right there, this is going over right there, going over right there, and things like that. Kind of cool. Anyway, giving you those nice little bits right there. Let's move forward. Okay, this is some of that module 10, and so is that cube root, but this is some of that module 10 stuff that if you go down to the link below, you'll get some more of me graphing some of the square roots and cube roots. I think these things apply just fine as well. Those also hit module 11, by the way. We will not hit module 11 here. We are going to identify the domain and range of these and sketch the graphs. Now, I'll let you know here, you can find the domain and range if you draw the graph first. You can find the domain before drawing the graph. You might want to wait to find the range before until after you draw the graph, though. The range is better identified when you see the graph for what it is. The domain can be expressed, though. See, domain is more about the equation because, and I'm going to find the domain first, especially for the square roots, because I just want to tell you about how square roots are a little different from cube roots. See, square roots are special in that you can't take square roots of negative numbers, at least not and get it represented on a real set of graph axes, right? You can't take square roots of negative numbers. You can take the square root of 0. You can take the square roots of positives. It doesn't matter if they're not perfect squares. You can do that. So it's not, I'm not asking you right now just yet what x can and can't be. What we have to say is what can or can't we take the square root of? See, this expression, this 25x minus 100 helps represent our domain. This 25x minus 100 has to be a positive number or 0. Right? It has to be a positive number or 0. And in that case, if I add 100 to both sides, and if I divide both sides by 25, x has to be greater than or equal to 4. This is the true domain of this thing. This helps represent why in your graphing form for this, your h is going to end up being 4. This helps explain why your graph ends up going to the right. And this also, I don't know if it really necessarily explains the range, but square root graphs are only going to be half parabolas. They're not going to be full parabolas because that's not a function. You should only be able to plug in one value of x, or when you plug in a value of x, you should only be able to get one value of y. So that's where the range is limited based on the domain's limitation in a way, because you can't take square roots of negatives, because a cube root has no problem having all real number domains and ranges, right? Because you can take the cube roots of negatives and they go up and down forever. But square roots, not quite. So x is greater than or equal to 4, that is the domain. I'll get you the range after I graph this. And I'm going to graph this after I get this in graphing form. My graphing form that I'm going to achieve for you guys is I'm going to obtain a vertical stretch factor. I will be getting a good old x minus h going on here. And I'll be getting a plus k right there. Now it's possible that you can get a negative inside of here. In which case, and unfortunately, I don't think I have a problem like this on this practice thing. I think that's why you need to go to the, go find another, go like and subscribe. Why you want to go check out that other link and look at some negatives when you have these here. But anyway, I'm going to get in this graphing form right here, which means I can't have this 25 in here. The 25 got to go. I want to represent this as far as a, this right here. That'll reveal my true h. That'll reveal my true vertex of what should be 4. And then I'll graph from there. So here we go, number 27. In order to do that, I must first factor 25 from here. And I'm left with x minus 4. And there's a minus 2 outside here. Now this is a square root of a product, 25 and x minus 4. You can, this is one of those radical properties that's in mod 11, you can take the product of two square roots like this, rewrite it like this. And I'm doing this because this is now my a value. I don't want to leave it as a square root of 25. I'm going to write it as 5. So now this can be rewritten as 5 times the square root of x minus 4 and minus 2. So this is a rewrite of this. This is now my proper graphing form for this. And I will graph based on what we know about this stuff. My h, k, and a. So my hk, my vertex. I still don't know. Someone's got to tell me. Is it still called a vertex when it's a half parabola? I'm just going to say it is. But my vertex, it's a reference point. My vertex is at 4, negative 2. This is where I'm going to start. 4, negative 2. This graph has a vertical stretch factor of 5. Even with my students, I often don't see something so large just because it goes off the graph so fast. But because this one's also going right and so tall so fast, might not be a problem. When you go over 1, you go up the square root of 1. But because it's a vertical stretch factor, I will also multiply that by 5. So instead of 1, 1, it's 1, 5. By 5, I mean 5 up from my vertex. When I go over 2, I'm not going to go up the square root of 2. I'm going to ignore that one. Square root of 3, I'm going to ignore that one. When I go over 4, I'm going to do that one. When I go over 4, I'm going to go up the square root of 4, which is 2. But I'm going to multiply that by 5. I'm going to quintuple that thing. So 2 times 5 is 10. So I'm going to go up 10 from negative 2 all the way up to 8. Oh, right on the corner. That's good. So boom, like that. And this is half a parabola right here. This thing is curving off into the square root of 25. It's curving off like that. I still have to find the range for this thing, and my graph kind of helps reveal that. First of all, does this agree with my domain that x is greater than or equal to 4? You betcha. These are the numbers that I can substitute into here that will guarantee 0 or positives that I take the square root of. See, if I plug in 3 into here, I get 75 minus 100. That's a negative. Can't take the square root of a negative. It's too small. In that case, I can plug in larger numbers, and we're good. So this agrees with that. So how about the range? The range, now that I have the graph, it kind of better shows that y has to be greater than or equal to negative 2. The graph goes up from negative 2 right there. You could determine the range if you understand that it has to do with the vertex and it's a positive and you go upward. You can come up with it. I just mostly state that unless you really fully understand every little bit about your graph, that you wait to probably get that vertex and graph it and know where it goes. That's a general rule about ranges. Domains are different because domains by default assume you can plug in any number for x in your function and there's no issue with it, unless you're dividing by 0, you're taking even roots of negatives like a square root or something like that, you're taking logs of negatives or 0. Things like that can limit your domain. But otherwise, you're often not limited in domain. So oftentimes all real numbers. That's why I'm saying your equation tells you those instances. All right, number 28. Y equals 5 minus 1/2 times the square root of x plus 3. As far as graphing form goes, it's kind of in that graphing form with the exception of the 5 is the k, right? I kind of want the 5 on that side. If you don't mind, I'm going to rewrite this as negative 1/2 times the square root of x plus 3, and then plus 5. The 5 is positive, the 1/2 is negative, and I'm giving it kind of its graphing due, right? I'm going to do that. All right, before I actually graph it, though, let's start with the domain. This inside thing, x plus 3, it has to be greater than or equal to 0. So I'm going to subtract 3 from both sides here. X has to be greater than or equal to negative 3. So you can plug in some negative values in for x. I need to find my water. Give me 1 second here. Give me 1 second. Okay, I'm back from my break, and when you need a break, go with Crystal Geyser. Not my #1 preferred. All right, you can plug in some negatives. I can plug in negative 2. See, negative 2 plus 3 is 1. I mean, that's good. Not too low. Anyway, so that one is my domain right there, and that'll make sense because my vertex is at negative 3, 5, right? That's the whole idea of flip keep. So I'm going to start there, and then I'm going to graph from that. So negative 3, 5. This graph also goes to the right. Like I said, if you want to see any graphs that go to the left, either find other things online or find my video down below. I think I do at least one that goes to the left. Okay, and then I apply the negative 1/2. Now the negative 1/2 stretch factor does a couple things. The negative says I do go downward. I don't go left, but I do go downward. This graph is going to have an appearance like this. But what are the points that I hit? When I go over 1, I take the square root of 1 to go 1 down. And the 1/2 means I'm taking half of 1. I'm dividing it by 2 vertically, not the horizontal. I go over 1, but I'm just going down 1/2. Half of the square root of 1. I go over 4 to 1, 2, 3, 4. I go over 4. Instead of going down the square root of 4, which is 2, I got to go down half of 2, which is 1. So you're going down half the square root of 1, half the square root of 4. And what's another perfect square? 9. I can reach that. So over here, I think, instead of going down the square root of 9, I'm going to go down half the square root of 9. So instead of going down 3, I'm going down 1.5 like that. And those are 3 distinct points that I can get. Plot on this graph. This is half a parabola. That top half that would go up and to the right, nowhere to be found. Ooh, I don't want to flatten out too much. Let me try that. Yeah, just as functions never go fully vertical, square roots and cube roots never go fully horizontal, right? They keep bringing themselves down. They flatten out, but they don't have asymptotes, right? Nothing like that. They never become fully horizontal. Oh, by the way, range. Here's the idea of the range. Just because it looks like it's flattening out, guys, it doesn't. It goes down forever, right? That's the important part. That's why it never goes horizontal. Y is less than or equal to 5 when it comes to that range right there. Okay, 5 is the top. It includes 5, and we just go down and forevermore. It's going to hit negatives. I just don't have the window range to show you. Stupid fraction stretch factor. Come on. All right, let's do a cube root right here. Y equals 3. Again, the k is kind of in front here, right? Y equals 3 plus the cube root of 8x minus 8. So I am going to rewrite that just for our sake here. And I need to work on the inside. On the inside, I'm going to work on some stuff. I'm going to add the 3 over, though. And I say work on the inside because just like that square root 1, I want to get an A. I want to get a vertical stretch factor. And it's going to be a perfect cube inside here that I can take the cube root of. So if I factor the 8 out, do they ask for domain and range? I guess so. I'll tell you about domain and range. All real numbers, all real numbers. We're going to go ahead and graph that. You'll see those. Cube roots are all real number domains. You can take cube roots of negatives, right? Anyway, I factor out an 8 from here, and I have x minus 1. And that idea is going to come into place again that, you take the cube root of this product, the cube root of 8 and the cube root of x minus 1. Well, the cube root of 8 is 2. So 2 gets to kick out, becomes my vertical stretch factor, and you get an x minus 1 here and plus 3. Now, for the informed that uses horizontal stretch and compression factors, a vertical stretch of 2 in this case also means a horizontal compression of 1/8. If there's an 8 inside here, everything becomes 8 times more shrunk in that way. And I can apply that. I can talk about that as we do this here. But anyway, so your center here becomes 1, 3. That doesn't restrict your domain, but it becomes 1, 3 right here. And the vertical stretch factor of 2 means you go over 1, you go up the cube root of 1, doubled. And perfect cubes, I got to go over 8. And then I'm going to go up the cube root of 8, doubled. So 8 is, it's off the map, or off the window, but I'm going to go up the cube root of 8, which is 2, and doubled, which is 4, like that. And negative, right? You go -1, you go down 2, right? There's that symmetry. If it's 1, 2, 8, 4, now it's -1, -2, -8, -4. And we apply the symmetry. We draw the curve. I'm going to do kind of a faster curve this time. Ooh, that curve's not very great. See, a cube root should flatten out to a 0 slope right there. Or in this case, an undefined slope, right? Not... Well, yeah. Yeah, sure. Horizontal compression. This thing is 1/8 what it normally would have been. You know how a normal cube root would have gone, you know, from here it would have gone 1, 1, and 8, 2. Well, now I took that 8, 2, and you know that 8? You take 1/8 of it. Now it became 1, 2. So there's that horizontal compression. This became 8 times closer to your reference point center right there for that horizontal compression. But I'm going for verticals. These are perfect cubes to do so. All right, let's see what we got. Oh, we got another cube root. Okay, so graphing. This one's already in graphing form. It's presented kind of perfectly here. So your center is going to be at -3, 1, right here on number 30. And stretch factor of vertical stretch factor of -3. This graph is going to go this direction now because it's upside down. Flip it over. And 3 times vertical stretch. So instead of 1, 1, it's 1, 3. Instead of 8, 2, it's 8, 6. 2, 4, 6, because we're tripling the 2. Instead of 1, 1 here, it's 1, 3. And instead of 8, I can't really fit this. 2, 3, or 1, 2, 3, 4, 5, 6, 7, 8. This one's kind of really off the map. It'd be somewhere up there. I just want kind of a decent guide of where this thing would go up to, so I don't feel like I'm just graphing wherever. Silly nilly. There we go. Kind of nice looking graph. I like when they get tall. Hey, domain is all real numbers. Range is all real numbers, right? This goes up and down forever. Okay. I don't even know if I'm doing the all real number symbol correctly. All right. Numbers 31, 32, graph each function. Now we're dealing with rationals. I think the next several are rationals here. And we're only 3/5 of the way through everything here. But maybe things speed up a little more. I got to slow down again because we're in a new set. Okay, as far as what we need to find here, for my students, because I haven't seen rationals for a while with you guys, but for my students, I like to get a lot of particular points, especially when we are in this graphing form, this y equals a over x minus h plus k. Sometimes you'll see someone write it y equals a times 1 over x minus h plus k, like that, either or. But the vertical stretch factor is still a. That hk is still that kind of reference thing. It's not an actual point though. It's actually the points of intersection of your asymptotes. We have a vertical asymptote and a horizontal asymptote to do here. And I got to identify some features for us, right? We got to figure out some information here. So when it comes to a vertical asymptote here, it's all about where are we dividing by 0, right? Where are we dividing by 0 here? And we are if x equaled 1, right? If x minus 1 equaled 0, then x would equal 1. This is the vertical asymptote. Now, x can't equal 1, right? That's a domain restriction. In fact, if they ask for domain and range, the domain is, I'm not going to talk about the range just right now, but x can't equal 1. But I'm going to write x equals 1 right here because they're asking for the equation of the line, what the line actually is. And the line is this thing right here, a vertical line. That's what x equals 1 means. There are no points that ever touch or cross this line. We leap over it to find other points, but there are no points on x equals 1 because that's where you divide by 0. Now the horizontal asymptote occurs at y equals k, at y equals -2 in this case right here. That's a horizontal line here. These are possible to cross in the mid-range, but for end behavior, this is where they start to converge at y equals -2. In these general ones, you're actually not going to cross it. It's when the graphs get more complex that there's a possibility. But at x equals 1, no, it's not going to happen. Now, what I do from here with my students is, we have an a value here of -2. A value of -2. And what's ideally happening is, this is my new origin. Every time that I displace myself x units from here, I'm going to be dividing my top value by that x. So if I go over 1 on x, I'm dividing -2 by 1. When I go 2 over with x, I'm going to be dividing negative 2 by 2. When I go over 3 by x, I'm going to be dividing negative 2 by 3. And those are the heights. Those are where I'm going to go on y, at least from this origin. So when I go over 1, negative 2 divided by 1 is negative 2. So I'm going to go down 2. When I go over 2, negative 2 divided by 2 is negative 1. I'm going to go down 1. Now, this point isn't really a great one, but if I go over 3, negative 2 divided by 3 is negative 2/3, right? It's like there. I wouldn't ask for those points for my students specifically. I like the negative 1/2 fraction, though. I think that's worth it. Negative 2 divided by 4 is negative 1/2. Because you know how to plot negative 1/2, you can stretch your graph out a little more and show that idea of approaching the asymptote. See, if I go over 100, negative 2 divided by 100, negative 1/50. It's getting really close to the asymptote that way. And I just like to show that convergence. And I like to show one if I go 1/2 over. Because what's negative 2 divided by 1/2? Well, that's negative 2 times the reciprocal, 2, which is negative 4. Basically, if I go 1/2 over, I will double this amount here, and I'll go down 4. So I like to show those halves when I can, and then just kind of show that approach as we get closer and closer, and we get a graph that, you know, that's kind of looking like that right there. Now, other teachers will tend to say you can plot and pick your points, and I could do this a lot faster. I will on the next graph and any other graph that we have on it. But they ask you to, you know, find your intercepts, find your x and y intercept. I argue I'm going to find them when I plot my points right here. If you ever want to find your x-intercept, you set y equal to 0 and solve for x. If you ever want to find your x-intercept or your y-intercept, set x equal to 0 and solve for y. But I'm going to find them by graphing them right now. They're not asking us to actually label them. So now I'll go to the left side. When I go negative 1, negative 2 divided by negative 1 is positive 2. So you're going to see your points go up here. So I'm not going to say negatives. Just here we go. When I go over 2, okay, 2 divided by 1. Excuse me, 2 divided by 2 is 1. I don't care about going over 3. When I go over 4, I'm going up 1/2. There's a symmetry. You guys see the symmetry here? It's going to be the same thing on the other side as far as that. When I go over 1/2, I go up 4 because I double that 2. I could, you know, I could, if I went over 8, 5, 6, 7, 8, I go 1/4, right? I can fit that. When I go over 1/4, I quadruple my thing. I go up right there. So you just get this idea. I like doing that with my students in Integrated Math 3 before they hit pre-calc with the really complex ones. And I know that some students in Integrated Math 3 classes get to the complex ones. I first want to introduce them not only the idea of what rational functions are and what they mean, but I'm also having this practice and preach the idea of the HK and the A and how those vertical stretch factors apply. No matter what kind of function, it still applies with the behavior of that particular function. By the way, x and y intercept are 0. 0, 0, and 0. All right, number 32. Let's go ahead and graph this guy. Now, your HK, H is 2, K is 1. Your vertical asymptote is at x equals 2. Your horizontal asymptote is at y equals 1. And we have this form. As long as it is in that graphing form, that is actually what we're doing when it comes to our graph. So I hope that you're kind of comfortable with that nature there. So let's go ahead and graph at x equals 2, at y equals 1. And everything, like that's my new origin. Watch how much faster I'm actually going to be doing this one here. This a is a positive 4. I'm going to divide from here. I'm going to divide 4 by 1 and get 4. I'm going to divide 4 by 2 and get 2. And I'm not going to divide 4 by 3. I'm going to divide 4 by 4 and get 1. I can't really get the half here. It would be at 8. I mean, I can. Like 8 is 1/2 like that. It's a little out of reach. I'll do it on this side. 1/2 over, I would double my 4 and it would kind of be up there. So you can kind of get those points right there. And you can see I didn't plug anything in. That's going to take a long time to calculate. So as long as you're in that graphing form, that can be achieved. But I'll tell you what, a lot of them aren't in this graphing form. I mean, these ones for my review are, of course, but outside of these, yeah, you do go for the features. You go for intercepts, you go for holes. I'm going to go for holes, but the rest of them are there. Now, -1, 4 divided by -1 is -4, and that's why this goes downward. So I'll just go down on these. Divided by 2 is 2. 4 divided by 4 is 1. 4 divided by 8, 5, 6, 7, 8 is 1/2. That's a good spot. 4 divided by 1/2 is 8. Did I say that last time? No, 4 divided by 8 is 1/2. 4 divided by 1/2 is 8. There's that symmetry that you have from the other side. You know, once you get them on one side, the other side aligns, so. But I didn't fit as many points on that side, really. All right, and there is our graph of that one. Do I have to mention anything else? No, that's it. All right, let's go forward. So we have two more rational functions to graph. Now we are identifying holes, vertical asymptotes, horizontal, x-intercepts. So I guess, okay, I'm going to be asked to find, I'm going to graph it, and I'll tell you what the x-intercept is, and I'll show you that the x-intercept matches with what we found. But I don't think this one has an x-intercept, actually. But let's move forward. Now for this one here, this isn't that graphing form. This isn't that f of x equals a over x minus h plus k. But don't behoove yourself into thinking that you can't get here. Look for common factors, and if not, look in a way you could do some long division as well. So this thing right here, I can actually rewrite this. You know, I can factor that bottom. This is x plus 4 on top, and on bottom, I have x plus 4 times x plus 1. 4 times 1 is 4, 4 plus 1 is 5, that's what it factors to. And you know, x plus 4 divided by x plus 4 is 1, sort of. There's a caveat, I'm going to tell you what that is in a bit. And therefore, f of x equals 1 over x plus 1. This is a simplified version of this right here. So these, for all intents and purposes, these would produce the same graph. Almost. There's one small exception. If you looked at it just straight on, you'd say, oh yeah, they're the same graph. The difference is, the first one right here presents a hole. This one presents a hole, and they're talking about identifying holes here. See, holes in vertical asymptotes are both domain restrictions. They are instances where you would be substituting a value for x where you divide by 0. Now, if you look at the original when we factored it, we would notice that x wouldn't be able to equal -4 and x wouldn't be able to equal -1. But when you look at this one, it just says x wouldn't be able to equal -1 as far as the domain. So the question is, which one do we go off of? Because someone might argue, well, the x plus 4 is canceled, so you got rid of them, right? So you don't have to worry about it just here. No, they didn't cancel. They became 1, right? Didn't I write a 1 up here? Right, they became 1. Because when you divide a number by itself, you get 1. But what if it's 0 over 0? Is 0 over 0 equal to 1? No. 0 over 0 is what's called an indeterminate. Indeterminates are just like undefines. It's division by 0. You can't do it. So if I substitute, see, this for all intents and purposes is the same as this, provided that we establish the fact that x is not allowed to equal -4. X is not allowed to equal -4, or of course still not -1, but this is where we get a hole. A hole exists at -4 for x, and in a way, there's a certain value for y that we will be stumbling across. I'll show you what it is on the graph when I do my graphing way, because we're in graphing form, by the way, and this is why we did this. You can substitute -4 into this equation and see what value we would have been approaching. The difference between a hole and an asymptote is that a hole has what's called a limit. That means that the left and the right side of your graph will actually approach that value and it'll jump it. It's not an actual point on there, but it is a reference for where it goes to. So I can substitute -4 into here, and f of -4 in this simplified version is 1 over -4 plus 1, which is 1 over -3, or -1/3. So it's going to hit at -4, -1/3 right here. Okay, that's a point that we are going to run into on this graph when I actually graph it. So that's where that hole kind of exists, right? Now, vertical asymptotes, those points diverge. They split and go up there, whatever, but they don't just go here and just jump that point. But the fact of the matter is, you can't plug this in for x. Remember, if I plug in -4 here, I get 0 over 0, indeterminate. But we're going to graph it like this, provided that the hole's there. Cool? Awesome. Okay, because I think this is the only, this one won't have a hole, because there's no 0 over 0. There's no canceled things. All right, so what else? Vertical asymptotes. The vertical asymptote is going to be at x equals -1. Remember, x can't equal -1, but that's the equation of the line. So the equation of the line there, x equals -1 is going to be like this. You know, as far as a plus k goes, you don't actually, you know, see a k value. That's because it's 0. And that's where I was saying I didn't think it has an x-intercept. This is, if you look at this, the numerator has a larger degree than the denominator. Therefore, this would have a y equals 0 horizontal asymptote. So horizontal asymptote is at y equals 0, as we know, plus 0 there. So we are going across like that. Okay, so as far as the graph goes for myself, for moi, I have a 1. That means I'm dividing 1 by 1 to get 1. 1 by 2 to get 1/2. 1 by 3 to get a third. These ones are harder to kind of do graphing things with. Even if I plot all these, it's like, what am I actually plotting? I can say that this is 1/5 with all my heart and kindness, but, you know, who am I to know? That's why I want to divide 1 by 1/2 for sure right here to double. 1 divided by 1/4 to kind of quadruple. I want to get some of the points up there, get some convergence toward these asymptotes right here. Closer and closer like that. And on the other side as well. 1 divided by -1 is -1. That's where we get that. And I want to get to the whole. So 1 divided by -2 is -1/2. 1 divided by, that's not a half. 1 divided by -3 is -1/3. Now, I'm not going to plot the point, but I'm confirming that that's where the whole is. That, and excuse me, it's not that the whole is an actual point, remember. So when I plot that, it's not that it's an actual point. It confirms that that's where your graph goes over, though. So we do want the reference point there. It confirms your limit value. There's no actual hole there. If you go to a graphing calculator, it wouldn't have like an open circle there. It would probably just have an opening, you know, like that. Or it might not have anything at all because, you know, remember, it's just at -4 that there's the actual hole. Everything else, -4.00001, etc., there are values, but there it is. There's still a hole. All right, that's it for number 33. Number 34, we have -x minus 2 over x minus 4. And, you know, this isn't in graphing form, and furthermore, there's nothing to factor. Yeah, I could factor a negative out of the front, but it doesn't, you know, it doesn't lead me to anything as far as canceling, as far as dividing anything on top and bottom. But I want that graphing form, gosh darn it. So what I'm going to do is I'm going to divide this. I'm going to actually use polynomial division. I'll just go and use long division. It's short enough of a thing for it to work it out. Numerator divided by denominator right here. And I'm going to see how many times does x go into -x. It's -1 time. X times -1 is -x. -4 times -1 is +4. And subtract, and -2 minus 4 is -6. So when it comes to rewriting this thing, yeah, -1 is your quotient, and -6 is your remainder. This divides, of course, by x minus 4. This is kind of graphing form. Of course, I tend to write it the other way, where the k is on the other side. So this is -6 over x minus 4 and -1, right? So this is our graphing form as far as dividing it. There was no hole. The division gives us a rewrite of this. These are equivalent. I didn't change anything. These are equivalent to each other. So when it comes to this, again, no hole, we have a vertical asymptote. Hold on. Did we need anything else? I'm sorry. Let me go back to this problem really quickly. X-intercept, I said there was no x-intercept. Y-intercept would be at 1. If you were, just really quickly, if you didn't know on the graph, if you wanted to find the x-intercept, what you would do is you would set y equal to 0. You could do it in either one. I recommend the simplified version because, as you notice, x plus 4 canceled. You wouldn't want to say, oh, there's an x-intercept at, you know, x equals -4. No, there's not. There's a hole there. So, you know, you want to make sure that you're not bringing up an x-intercept by setting y equal to 0 and solving for x in that situation. You want to instead set y equal to 0 here. Set the numerator actually rather equal to 0. In this case, and 1 equals 0, and that's impossible. So there's no x-intercept. So the x-intercept in this case was none. And of course, with the horizontal asymptote of y equals 0, I'm not saying how could have there been, because of course, like I said, there are some graphs that exist that can actually cross the x-intercept and go back. Not these simpler ones, though. Not the simpler ones. So with this one here, back to 34, vertical asymptote would be at x equals 4. The horizontal asymptote on this, in this case, based on this graph, is y equals -1. So let's start with those parts on the graph. X equals 4. Y equals -1. And, you know, honestly, I could go straight through this graph and bam, 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 and I'm going to get some of that in for you. I am going based off my graphing form right here. I got the -6 going. So as far as -6 goes, -6 divided by 1 is -6. Down here, -6 divided by 2 is -3. -6 divided by 3 is -2. And kind of unfortunately, I'm going off the graph here. I really like to have as many of those integers as I can fit. -6 divided by 4, 5, but -6 divided by 6 is -1, see? So I want to kind of at least get that point. On the other side, I'll have plenty of room, I do believe, for this vertical stretch factor. So -6 divided by -1 will be going up 6, +6 right here. Divide by 2, you get 3. Divide by 3, you get 2. Divided by 4, 5, 6, you get 1. I can divide it by 12. I get 1/2. Check that out. I can fit that point. So kind of cool that that actually goes that far. Now I'm actually kind of excited to see that. And let's get that one going there. Now, you know what? I am going to divide it by 4 because I want to tell you about the y-intercept. And of course, how you can get the y-intercept here. So this y-intercept right here, what would have this been? -6 divided by 1, 2, 3, 4. -6 over 4 is -3 over 2, or -1.5. So this is -1.5 here. The x-intercept was clearly -2, 0 based on my graph. The y-intercept, as I showed you just by dividing, was 0, you know what? 3/2. I'm sorry, not -3/2. It was -4, so +3/2. It's 3/2 up from the asymptote, so it's just one half. It's just 1/2 right there, right? That's the actual point. So 1/2 up from there. If you want to find the x and y intercepts by, calculating them, not with the graph thing. Once again, for the x-intercept, what you would do is you would set y equal to 0. See, this is not a simplified version. This is a rewritten version. Simplified meaning I canceled things out here. I would actually want to do it with the original in this case, and anything I could factor. But what I do is I set the numerator equal to 0, because I don't care if the denominator equals 0. I care what gives me 0 on the top, right? That's the whole idea. So add 2 to both sides. -x is 2. Actually, add x to both sides. X equals -2. So x equals -2. That was my x-intercept. Setting y equal to 0. With the y-intercept, you set x equal to 0. You get, right, 0, 0. -2 over -4 is 1/2. So y is 1/2, or 0, 1/2. So that's how you do those ones right there. Anything else? Hold. Nope, we got them all. And that is our graph. These can take a while. They can be fast, all depending on what you're doing. Obviously, I was teaching through it. But we went as fast as we probably possibly could, as well as getting as many points as we could. That was a lot of points, guys. I got like 20 points there. All right. Now, more rationals here. And this is where I said I was going to go faster with the factoring of quadratics. I'll explain some things, but I'm not going to dive deep into strategy unless I feel there's something new being covered. All right, this is just a straight up fraction. Simplify each and state the excluded values. Now, simplifying means finding common factors that exist on top and bottom of this thing and, canceling them, dividing them, making them become 1. Excluded values, there's another word that I use called restrictions. Restrictions and excluded values are values where at any point in time in your simplification, in your expression, that you would have been dividing by 0. Those are values of r, of n, of v, of x that you cannot have ever. All we're doing, see, we're not solving for a variable. We're stating that this is going to be equivalent to whatever we simplify it to, and that these are r or x or whatever values that could never have been plugged into this thing. That we could never try them because we'd be dividing by 0. Even 0 over 0. Even the canceled factors. So let's go and try and factor top and bottom. On top, I do have a common factor of 2. And if you factor out the 2 there, you get 7r squared minus 22r plus 3. And on bottom, you have... well, I can start factoring this if you want me to, and then I'll factor the top afterward. 5r squared is going to be some form of 5r times r. This is a positive product and a negative sum, so I know this will be a minus and a minus. Now I have an odd number here in 19, 12 being 12 times 1, 6 times 2, or 4 times 3. Means that 6 times 2 is out because that would give me an even plus an even, and that is an odd. So it's either some form of 12 times 1 or 4 times 3. 12 and 1 had a shot right here. If you tried 12 and 1, that's -5 minus 12, which is -17. Very close, but it's not it. If you put a 12 here, you get -60. That's not it. You try 4 here, they get -20. It's too far. You try the 3 here. This should work. -15 minus 4 is -19. Whiz bang, whiz bang, whiz bang, right? That's what I'm going for. Let me factor the top now, this whole 7 mumbo jumbo. And actually, not only is this one easier in general because these are both prime numbers, 7 and 3 are both prime numbers, but also here's another factoring strategy for this bit that I really want to talk to you about. I'm really excited to as well. Okay, first of all, minus and minus because the positive product negative sum. If they're asking us to simplify, it is more likely than not that there are factors that are going to at some point cancel. that there is something on top that will be able to divide with something on bottom. It is worth it for you. It is of your best interest to consider when you're factoring something that's more complex, like one of these where like, does it go here, does it go here, which numbers, that you try some things that are on bottom that have the potential to factor, provided that it would fit the factorization right here. Like for instance, you see this r minus 3? What if this was r minus 3? What if this was r minus 3? Like, then those would cancel, right? Does this fit the narrative that this could happen? Absolutely. You know why? This is a 3 right here. These are negatives. If this is a -1, then -1 times -3 is positive 3. Now, is this the answer? I don't know. Let's see. -21 minus 1 is -22. Yes. So strategically, what you want to do is find things that you can factor easily and lead them to other things that you want to try and factor and see if they work, because it's possible that they do. And if it doesn't, well, you tried something, right? You tried something anyway. You had to try things anyway. You might as well try the ones that can potentially cancel things. And by cancel, I mean become 1. r minus 3 and r minus 3 cancel. And you are left with 2 times 7r minus 1 divided by 5r minus 4 as a final result there. Keep in mind, as a multiple choice test, it is possible that they could write the final answer as 14r minus 2 over 5r minus 4 because they could distribute the 2 back in. Keep that in mind as a multiple choice test. You don't get to pick and choose what the answers look like. You just got to find the one that matches something that's correct. So this or this are both appropriate. We're also not done. We got to get excluded values, restrictions. The values are the bottom can never have equaled 0, this denominator. So you know why we also factor? Because we want to know that this denominator here, we can use zero product property. And we say, if 5r minus 4 times r minus 3 can't equal 0, then 5r can't equal 0. Excuse me, then 5r minus 4 can't equal 0. Therefore, add 4 divided by 5, r can't equal 4/5. And r minus 3 can't equal 0, therefore r can't equal 3. These are the two restrictions. Sorry about the room. These are the two restrictions to this thing right here, the two excluded values. All right, maybe we can move a little faster now with these problems now that we've done that one problem. Number 36. Well, on bottom, I clearly have a common factor of 4 where we get n minus 3. On top, we actually do have a common factor. It looks like of 2n right here, and we're left with a quadratic. That is 7n squared minus 31n plus 30. And this thing is leading itself for me to try something that I want to try again. What do you think I want to try here? So there's a 2n on the outside. We know that we have this 7n times n. Oh, by the way, actually, hold on. Before I even talk about 2n, 2 divided by 4 reduces to 1/2. Don't forget to do that as well. Those count, right? Those count for something. So there's no 2 more. There's no 2 up here anymore. So there's n right here. Now I have 7n times n to give me 7n squared again. Positive product, negative sum gives me a minus and minus. Down here I have 2 times n minus 3. What do you think, and I haven't tested this yet. I don't even know if it's going to work. Now I do. What do you think I want to try first? I want to see if this n minus 3 can cancel with a potential n minus 3. And n minus 3 can fit this narrative because negative 3 times something gives us 30, which is negative 10. Let's see if these combine to give us negative 31. 7 times negative 3 is negative 21. Negative 10 times 1 is negative 10. Negative 21 minus 10 is negative 31. Yes. So without trying too hard, 30 is 30 times 1 and 6 times 5 and 10 times 3. Without trying all those things, I worked strategically with something that potentially could work, and it did. And thank goodness it did. I didn't want just 2 over 4 to reduce. That would not be fun enough for me. So anyway, this does equal n times 7n minus 10 all over 2, which of course they also could have put 7n squared minus 10n all over 2. This is also possible. Again, who knows what multiple choice is going to say. Because the idea is if nothing else could factor up here, then there's no reason to have factored. Technically, simplified generally means no parentheses around your things, but we are going to ignore that for some larger things that come about in these factors. Okay, whoa. Okay, I need to move these up for when we do the next problem. After I list my restrictions here, the restrictions for this one are, or the excluded values, n could not equal 3. Now, I want to remind you, you can have 0 on top. There's nothing wrong with dividing 0 by a non-zero value. There's a problem with dividing 0 by 0, in which case whenever you have a whole, such as, these r minus 3's canceled. I didn't really mention that. R can't equal 3. I know that we have a simplified version of it where you could plug in 3, but it's all about the original expression or any expressions within as you do your work. R can't equal 3 because 0 over 0 is a problem, right? These are equivalent, except here r can't equal 3, and we have to make sure that we state that in this equivalent simplified version, r still is not allowed to be 3. Anyway, so n can't equal 3 there. But n can equal, 0. N can equal 10 sevenths, right? Because you can divide 0 by numbers. Okay, number 37. Now we have a multiplication. Now in a product of fractions, you can totally, without issue, you can totally divide things. Like, you can totally treat this as one fraction. I tend to not write it as one fraction, but you can treat it as one fraction. That means things over here can divide by things over here just as much as they can divide by things over there. I just want to let you know that. Okay, and by the way, those are quantities. So I'm going to factor a 6 out here as a common factor, and I get v minus 1. And here I have v minus 1. And we're going to multiply by it. This is factorization. What's known as multiplied negative 24. Now to make negative 2, that's negative 6 and positive 4. And there's a common factor here of 6, where we have v plus 4. Now, I'm not outright trying to multiply and FOIL these things, right? Multiplying just means bring it all as one fraction. So right now, technically, this could all be, like I said, one big fraction. This times this times this times this, or this times this. But keeping it separate's fine. Just know where things go. For example, I do have a v minus 1 over v minus 1 right here. Those are fine. But I do have 6 over 6. 6 over 6 is 1. I'm going to get rid of those. And v plus 4 over v plus 4. And I'm just left with v minus 6. Ultimately, that is the simplified version of this, provided that we still list our restrictions, those excluded values. Last time I said excluded. This time I'm going to say restricted values. V cannot equal 1. I don't care that it canceled. 0 over 0 is not allowed. V cannot equal negative 4. I tend to just write it as one list. V cannot equal 1 or negative 4. I got so hung up with the x equals equations of vertical asymptotes that I don't know. All right, so those are our restrictions there. Okay, that's it. Number 38. X minus 6 is exactly as it's going to be. Oh, by the way, this is division. So I'm going to state this. Division is multiplying by the reciprocal of the other guy, but I'm not going to flip it yet. I'm going to factor first. I'll explain why in a moment. I'll see if it's actually relevant to what we're talking about. Actually, I think it is. Keep it as division. You don't have to. I'm going to state why I'm doing it for the sake of those who might need this. Factor the top here. This will be x minus 6 times x plus 1. And on the bottom, there's a common factor of 3 and all of x plus 3. Now, just to be careful of things, while this is division, we're not trying to find things on top. Like if this was an x minus 6, I'm not going to go like, oh, cancel those. No, the division still means just don't cancel anything yet. I don't care if something can cancel immediately on top and bottom right here. Just don't do it yet. Just wait. Now I'm going to go ahead and flip it. And on the flipping stage, that's where I will be dividing common factors on top and bottom. So now we're going to multiply by this reciprocal, and we'll get 3 over x plus 3 over, or 3 times x plus 3 over x minus 6 times x plus 1. So now, with proper multiplication, now something here is dividing by something there. X minus 6 over x minus 6. 3 over 6 reduces to 1/2. And I think that's it. And you're left with x plus 3 on top. And 2 times x plus 7 times x plus 1. So that is the simplified result. Oh, never mind. This thing didn't apply like I was hoping it would. Okay, restrictions here. X rest. X cannot equal, surely it can't equal negative 7. And it can't equal negative 1. Whoops. I'm thinking about the next number ahead. It can't equal negative 1. And it can't equal 6 because of that whole issue. But you know what else it can't equal? It also can't equal negative 3. Now, before you might say, Mr. Robinson, before you just said that you can have 0 on top. You can plug a negative 3 because you get 0 over a non-zero number. Yeah, that's right. But what I also said was you can't ever divide by 0 at any point in your expression. That includes the original expression. And you know where the original expression has trouble with -3? Oh, I'm sorry. There's an issue with the thing. You know what? I screwed up the problem. Oh, I'm sorry, guys. I screwed up the problem. I can't edit this out. But let me state this. Let me state this, and then I'll change it. I was going to say, you know, right here. See this factored form right here? The -3 plus 3. That would have given you 0 dividing by 0. Yeah, we flipped it. But there was a time where this would have been an issue. Now, I gotta change this. There's an error here. You factor out a 3. That's not x plus 3 anymore. Okay. This is going to change a few things. This is totally my bad. You're probably looking at this going, oh, what is this guy doing? But that's why we get to talk through it, and that's good. I got to make that point. I'm glad I did. And I'm going to say, I don't want to cancel the x plus 1s yet. You just hold off. Because I don't want you to cancel something later that you regret not being able to. So anyway, this is now an x plus 1. All right, things will change. I was sitting there thinking, this is a little bigger than the other ones here. So x plus 1s do divide. Hey, what's left on top now? You know what a lot of people, you know what, actually it's a good thing we're doing this too. You know what a lot of people tend to do on this kind of problem? You know whatever's left on bottom, 2 times x plus 7, they would just say, hey, it equals 2 times x plus 7. No, see, that's the problem with saying that things cancel. The division didn't cancel. These are still in the denominator. You're still left with a 1 up here. This is 1 over 2 times x plus 7. I'm still glad I made that mistake because I got to talk about what was before and I get to talk about what's happening now. So that's the answer. Yeah, x can't equal -7, still can't equal -1, still can't equal 6. You know what? It can equal -3 now. You're okay. But my point was, right here, when it was factored right here, if this x plus 1 never canceled, that's the time when you're dividing. And if you're dividing by 0 there, you got to make sure that there's a restriction there that is involved. Okay. I've spoken enough on that one there. I am probably going to be hitting that 3-hour mark, rest assured here. I never thought that would be the day. You know, with the other stuff, we did like 150 problems or whatever it was. I was just stating to that group, I said, because it's so many problems, I'm not going to make it like a 6 or 7 hour video. So I'm going to speed that up. These ones have a lot of different things going for them. And I feel like I'm teaching to a larger audience in the Integrated Math 3 group that they need to hear the teaching. All right, number 39. I have 6. Okay. This is v plus 10 times v plus 7. No more mistakes for Mr. Robinson the rest of the way. Can he do it? Divided by, notice I'm doing the divided by here. All right, common factor of 5v, and I'm left with v minus 9. And now down here I have v plus 10 and v minus 9. Okay. All right, before I cancel anything, let's go ahead and flip this thing over. 6 over v plus 10 times v plus 7 times, not divided by anymore, v plus 10 over v minus 9 over 5v times v minus 9. And, you know, once again, you might be asking, well, you know, why didn't you cancel these? You're about to cancel them. I know. Let's just get a canceling stage. Again, I don't want you to accidentally cancel something else up here that you, if this had a 5v and 5v, because those wouldn't have been able to. Anyway, now they're gone. No worries. They're gone. V plus 10, v plus 10, and nothing else. If there was like a v up here, yeah, those would go away, but it doesn't, so we won't. So we won't. So we are left with 6, just 6 on top, and I got a 5v on bottom and a v plus 7 on bottom. All right, what are our restrictions here? What are our excluded values? What can't v equal? Well, you know what? V can't equal 0. People seem to forget that one. Sometimes people put 5, like -5, things like that. No, v can't equal 0, right? 5 times 0 that is 0. -7. And you know what? Actually, go for these ones first. My students are actually, they actually remember to do these ones. They forget to do the ones that are here. It can't equal 9, and it can't equal -10. Check on these. Okay, these are ones that went away, right? Can't equal those, but we already took care of them. All right, those are our restrictions for v. Okay, those are the multiplying and dividing. Are we adding? Yes, now we're adding and subtracting. Now, adding and subtracting, what we have to do is we have to find a common denominator. There are a few different steps in these ones. For one, I'm not going to ever worry about factoring the top, even if it was this nice, fun quadratic, even if there was a 2 right here. Excuse me, even if it was like 2n minus 2 right here, and I could factor that out. I'm not trying to factor the top. I'm actually going to keep it as expanded as possible because I want to end up combining like terms with other things so that maybe potentially as it's simplified as an expression, a single expression in one fraction, maybe then I look to factor something. Until then, I'm going to try and combine them, but I need to factor the bottom in cases not only to attempt to find a common denominator, but also to find my restrictions, because there are still restrictions. Now, these have a common denominator, 9n squared plus 81n plus 180, and that's huge. So I'm still going to factor the bottom, though, because ultimately, I still need to find restrictions. They didn't ask us to, but you still need them. So, what can't n equal? So on bottom, I'm going to factor 9 out of n squared plus, actually, let me do this on top. Factor 9 out of n squared plus 9n plus 20. And that's going to factor into 9 times n plus 4 times n plus 5. Okay. Now, this is a common denominator, by the way, folks. So I'm already going to be able to write this as a single fraction. And straight up, we can add straight across the top. N minus 2 plus 2n. Okay, so working that out, this will leave us with 3n minus 2. And on bottom, we have 9 times n plus 4 times n plus 5. Now, this is one of those opportunities where you ask yourself, is there something I can factor out on top so that there's potentially something to reduce on top and bottom? And I haven't mentioned this yet, but I have a lot of students where, and hopefully you're paying attention now, or hopefully you've been paying attention so far. I can't just turn this 3 over 9 to 1/3. I can't do that. 3 was not a common factor on top. I didn't factor a 3 out of these two terms. If you divide this by 3, then you got to divide this by 3 as well. And that's not something I'm willing to part with and build a fraction off of. If this was the case, yeah, you'd factor that out to 1/3. But 3 is not a common factor. We factor to divide common factors, right? We don't have something where it's like x plus 7 over x minus 2, and we just cancel out the x's. That's not how that works. Common factors, work that thing out. Anyway, bottom line, I didn't build these problems necessarily. A program did, so you are probably going to see some instances where, maybe things don't cancel factor on top and bottom, and we're going to have to live with it. And if they do, it's kind of special and it's rewarding. I think that you feel like you're doing a lot more when that happens, and we'll see if we do. I haven't done the problems yet, so I couldn't tell you if they do or not. All right, number 41. We don't have, I'm going to rewrite it just to give myself space. We don't have a common denominator on bottom, so you can't just add straight across. There's nothing like that. So we have to find a common denominator. Basically, as we see this factor of k plus 1, we have to ask ourselves what's missing in the other, thing. We got to find a common denominator. So we are going to multiply this fraction, top and bottom, by k minus 5. You know how common denominators work. You got to multiply top and bottom by the same thing because we got to be multiplying by 1. We can't change this value. We're just going to change its appearance. And here we're going to multiply by k plus 1. That way, we'll get a common denominator of k minus 5 times k plus 1. So now, when we go across the top here, it'll be one thing we can go across the top. We can add and combine like terms. I'm going to keep the bottom factored. Oh, I didn't do restrictions. Oh my gosh. Hold on. Restrictions. Right here, n can't equal -4 or -5. My bad. Okay. Anyway, so right here, we'll keep it factored so we can talk about restrictions. And there's really no need to do. And in fact, one other reason we keep this factored, because in case something can factor on top and we can do the cancel thingy, we have this thing factored and ready to go. So we'll just keep it factored the rest of the way. We're not going to touch this part, but we will distribute the top. We'll distribute the top because what we need to do is start combining like terms up here. 2 is multiplying with k minus 5. 2 will distribute into k minus 5, and you'll get 2k minus 10. And then 4k multiplies with k and 1, and we'll have 4k squared, quadratic, 4k squared plus 4k. Now when you combine like terms, you get 4k squared plus 6k minus 10 over k minus 5 times k plus 1. There's a common factor of 2. So here's kind of the tricky part. I don't know if this thing right here is going to be factorable. For all we know, it's not. Let's see how I say this. Our only need to factor this is if something can reduce on top and bottom. So there is a little bit of a strategy that I'm going to be able to play with here. First of all, there is a common factor of 2. So I'm going to start with that. And I have k squared. Let me do this on top as well because I don't have much room. So I'm going to do, that's 2 times k squared plus 2 times 2k squared plus 3k minus 5. So we're going to try and factor, because I don't know if it's factorable or not. I can look at it and try and decide. I have no idea. Actually, now I do know. But so when we try and factor this thing, remember, the goal isn't to factor it. The goal is to see if there are factors that exist the same on top and bottom. So my strategy is going to be this. First of all, we know it's going to be some 2k times k. And with minus 5 here, we have to make sure that we're kind of trying to plug in values that kind of work here. So here's the idea. I want to, and both of these are worth trying, apparently, because k minus 5 and k plus 1. I want to decide, is this potentially a k plus 1? Because if it is, then that means that I can cancel out the k plus 1s. Or is this potentially a k minus 5? Because then I can potentially cancel out the k minus 5s. That's all I care about. If there was any other factor in the business, including k plus 5, including k minus 1, I couldn't care less if it factored. I couldn't care less. This is a fine answer if this is not factorable, because nothing could cancel on top and bottom. I only care about these. So let's try k minus 5. Oh, in guess that's k plus 1, right? Because this was a minus 5 there. Negative 10 plus, nope, that's not going to work. Let's try k plus 1 and minus 5 here. And that's going to be 2 minus 5, which is negative 3. Well, we needed a positive 3. Now, I'll tell you what. This was factorable if this was a plus 5 and if this was a minus 1. It was factorable. Do I care? No. Oh, the only reason I'd care, I take it back. The only reason I'd care is if in a multiple choice test, this was one of the things. But otherwise, this is perfectly simplified, or the distribution of k minus 5 times k plus 1. I'm not going to show you all the alternatives, but do I care? No. Nothing here cancels. K minus 1, k plus 1, guys, they don't cancel. Obviously, that doesn't cancel there. So this is what this would have done, because negative 2 plus 5 is 3, right? So that would have factored to that. So it does factor. Bottom line is it doesn't cancel. So you know what? This is a good answer. This is a good answer, but I didn't cancel anything, so there's that. All right, restrictions. I'm just going to nice and bold here. Restrictions, k cannot equal 5, k cannot equal negative 1, right? Those bottom things divide by 0. Okay, assuming I didn't mess anything up. It's very possible I could have messed something up because it was so close to factoring. I was sitting there thinking, maybe it is. Maybe it is. I don't know. Looks good, though. Looks good to me. Okay, here we go. I'm trying hard to hit that 3-hour mark, aren't I? All right, 42. I got 9 more problems here. Solve each equation. Remember to check for extraneous solutions. If we get a solution that would have made us divide by 0, it's considered extraneous. All right, we are going to go for common denominator here once more. On top, I have r plus 6. On bottom, I factor a 2r out, and I get r minus 2. On top, I have a 1. On bottom, I have a common factor of r. I have r minus 2. And this is 3 over r. Okay, so we are trying to seek a common denominator. We need to make sure that we inherit every part of a factor that's missing in any of these guys. It looks like this thing has the whole package. This thing shares an r right here with all these. It shares an r minus 2 with this guy, and this has a 2 that these guys don't got. So this thing needs to multiply by 2 over 2 right here. This thing not only needs to multiply by 2 over 2, but also, this thing also needs that r minus 2 that the other guys got. So 2 times r minus 2 also needs to be done right there. Okay, so there's a lot of work to kind of be had with this still. Now, I'll tell you what. Now that you have a common denominator in an equation, 2r times r minus 2, 2r times r minus 2, 2r times r minus 2, I'm going to multiply both sides by 2r times r minus 2. And you know what happens to the denominators? They go away. Now, they go away in the sense that we got to make sure that any extraneous solution, that any solutions wouldn't have us divide by 0 in the original equation. But I'm going to multiply both sides by that to make it go away. I'm not actually going to multiply both sides by it. I don't care. I couldn't care less about actually stating that. If they all divide by the same thing, if they're equal when they all divide by the same thing, then they're all equal when they don't divide by the same thing. Therefore, I'm going to ignore the denominators the rest of the way. Now, I can only do this because it's an equation. I cannot do that in an expression. You never saw me do that in a single expression ever. just ignore denominators. I am now in that I'm multiplying both sides by this. So by denominators, you did their work, provided that now I'm going to multiply these things. So I have an r plus 6. I have 2 times 1, which is 2. And this equals, so 3 times 2 is 6, right? So 6 distributed into r is 6r. And 6 times negative 2 is negative 12. So here is our equation. There's a mistake here. Oh, no, there isn't. I'm sorry. I thought this was me multiplying a common denominator by r over r. I'm sorry about that. No, we're good. Sorry about that. Okay, so here we go. Let's combine like terms. I got r plus 8 equals 6r minus 12. Yeah, listen, you know this work right here, right? 5r equals add 12 is 20. Divide both sides, r equals 4. All right, we got r equals 4. Was 4 ever a problem? Does 4 present an extraneous solution? Does plugging in 4 into the denominator in factored form give us 0? The answer is no. So r equals 4 is not only a valid solution, it's the only solution to this thing that makes the statement true. We're not just simplifying something, saying r is all real numbers. So, you know, there's sometimes where people say like, oh, r equals 4, and r can't equal 0 and 2. No, duh, r can't equal 0 and 2. R can only equal 4. R can't equal 7 either. There's only one thing. I understand why you're saying this. You want to make sure that extraneous solutions aren't put in. But stating it after the fact is whatever. R can only equal 4. 0 and 2. Who cares? All right. It only matters if you actually got r equals 0 or 2. All right. Last one, solving a rational here. Number 43. I got a bottom thing to factor there right now. Let's go at it. X plus 4 on top. And on bottom here, I know, because of the whole even odd argument, this cannot be 2x and 2x because I have an even number, I have an odd number here, and 2x's would give me evens. So if factorable, this is a 4x times x. There's some sort of plus and minus. I don't know where they go yet. And the 9 is going to have to come from some sort of, I think 3 and 3. If I plug in a 9 and 1, it's not going to get me that negative 9. So I'm going to try some form of 3 and 3 here. Negative 12 plus 3 is negative 9. Boomskis. Same factor right here. This is going to be 4x plus 3 times, times x minus 3. Oh, and I have to talk about something else. This is related to my students as well when we do this next problem. Okay, darn, we're not solving a quadratic. Okay, these both have a common denominator. This one's missing an x plus 4x plus 3, right? So multiply top and bottom by that. Okay. What I wanted to talk about has more to do with expressions than equations. Let me go back to something really fast here. Don't worry, I'm gonna go right back. When we had to find a common denominator. Oh. Okay, so let me go back to this problem right here. You know, some of my students wouldn't have distributed just yet. I'm sorry about this. I need this pause. I should have mentioned it at the time. Some of my students wouldn't have distributed yet. They would have written 2 times k minus 5 plus 4k times k plus 1, all divided by k minus 5 times k plus 1. And then what would have happened is they would have canceled k minus 5s and k plus 1s, and they would have gotten 2 plus 4k. I promise you, I saw this so many times that I stopped grading one night and I just said, I'm done. Like, I don't even know what to do. This was frustrating me a lot. Two levels of frustration. First one is you cannot do this. K minus 5 is not a common factor in the whole top quantity. It only is with a 2. Once this plus is here, that denotes your ability to cancel these things out. That's a pretty big frustration. Second big frustration is this. Why did you bother multiplying top and bottom by k minus 5 if you were just going to cancel k minus 5s after? And furthermore, why did the expression suddenly change? Before it was 2 over k plus 1 plus 4k over k minus 5. Now it's just 2 plus 4k, where the denominators are gone. So you can see that, you know, why do we multiply them just to cancel them? Why do we multiply them just to cancel them? So have common sense in what you're doing and what you're approaching. Please keep in mind what the tactic is up here. You actually want to distribute them as you're working them out. And that canceling is not only not allowed, but it's counterproductive to what you literally just did. Okay. Anyway, sorry about that. So let's keep going here. Common denominator. I'm done with the denominator. except for restricted values. Keep in mind restricted values. All right, so x plus 4 equals 5. Now here's you got to be careful. You're going to distribute a negative 1 into 4x and 3. It is a negative 1. Negative 1 times 4x is negative 4x. Negative 1 times 3 is negative 3. So 5 minus 4x minus 3. Now remember, I got rid of these denominators because the equation. I multiplied both sides by the denominator. Okay, I'm going to add 4x. Simplify this side. Negative 4x plus 2. Okay, I'm going to add 4x to both sides. You get 5x. Subtract, I hope this is right. Subtract 4 from both sides. You get negative 2. And you divide both sides by 5. You get x equals negative 2 fifths. I'm going to have to trust it. I just want to triple check that there wasn't anything I should have got different. Common denominator here, x minus 3, 4x plus 3, negative 1 times 4x plus 3 is negative 4x minus 3. It's just sometimes when I get a fraction, I'm like, I want to make sure I did right by you guys on that. You know, it didn't screw anything up. I'm going to say it's good. By the way, negative 2 fifths is not a restriction, is not an extraneous solution. 3 would have been, negative 3 fourths would have been, and negative 2 fifths is fine. All right, number 44. Describe how the graph of f of x equals x cubed is related to the graph of f of x equals negative 1/3 times x minus 7 quantity cubed plus 1. What they're asking you to do is describe the transformations that you would do to go from this one to this one. And honestly, where this thing says f of x, you probably should have a different function like g of x, especially if you want to describe from one to the other. So I'm going to just do that. I'm going to call this one g of x instead. So I'm going to type this one out here. So just describe what's happening here. So the negative on that stretch factor, vertical stretch factor, is basically us reflecting across the x-axis. So we're going to reflect f of x across the x-axis, and that's one thing that's going to help make it become g of x, right? That's one of the things. We are also going to vertically compress f of x by a factor of 1/3. Everything's going to be 1/3 the height that it previously was. And the negative 7, the 7, 1 center of this cubic function would be a translation, 7 units to the right and 1 unit up. Translate, I'm not going to graph it, but translate 7 units right and 1 unit up. Now, when I graph these things, you know that I start with the translation, but that's because I fixate everything along that point. You must, in a description, in terms of doing it properly, you must describe the A value stuff first and horizontal things first. Vertical and horizontal stretches, compressions, and reflections have to be stated first because your equations don't know, your graphs don't know that when you're at the point 7, 1 that you're treating it as 0, 0. It thinks of it as 7, 1. So if I reflect it, that would become 7, negative 1. If I compress it by a factor of 1/3, it becomes 7, negative 1/3. It doesn't know that you were just keeping it there as you did the other things. Just keep that in mind. All right, that's the description for that stuff here. Okay. Number 45, identify the zeros of each polynomial function. We've talked about zeros in the past. You set the y equal to 0 as you solve for x, and this is where we get polynomials. I believe these are the last kinds of questions that we have and that we're playing with here. So I'm going to set this all equal to 0. Zero product property is in full effect here, and these are the equivalents of the x-intercepts we find when we do these polynomial functions right here. So if this times this times this times this squared equals 0, either this equals 0, or this equals 0, so x minus 2 equals 0, so x equals 2, or x plus 4 equals 0, so x equals negative 4, or x plus 5 squared equals 0, so x plus 5 equals 0, so x equals negative 5. And that one is special. That has what's called a multiplicity of 2. That doesn't matter for our zeros, it matters for our graphs. So just make sure that you know that this one, having a multiplicity of 2, is something we're going to be playing with, even with, with regard to right here. And that's it. There are the zeros. When we graph these, we want to find those zeros. You don't have to write set equal to 0 to do that. You just got to know what it means. All right, write the equation for each polynomial function. All right, function. What we want to do is we want to establish those zeros. This is essentially going to be reverse of what I just did when I found those zeros. Let's establish what those zeros are, and let's write them in their factored form equivalent, understanding what their multiplicities are. So I have a 0 here at x equals negative 1, and it goes through in a linear fashion, which means that has a multiplicity of 1. That's one of my x-intercepts, one of my zeros. I have a 0 at x equals 0. This one bounces off. It has that parabolic nature to it. This one has a multiplicity of 2. It could potentially have a multiplicity of 4 or 6 or 8 or whatever, but it's okay. You can have a, what do they say? Write an equation. Just, you can have the least degree. It's an even degree bounce. That's all we care about. Another 0, one more 0 at x equals 3. It also bounces off. This also has a multiplicity of 2. Now, when you have those zeros, they're factors. You just saw it in this other sense. When x was 2, it had a factor of x minus 2. When x was negative 4, we had a factor of x plus 4. So you have, one opposite of it. If x equals negative 1, then x plus 1 equals 0 is one of those things. X plus 1 is one of your factors. X equals 0, x is one of your factors. I like to write that in front. It's kind of, it doesn't have parentheses, whatever. But it's actually x squared. It has a multiplicity of 2, right? So it's actually x squared. Ugh. And x equals 3, x minus 3 is one of your factors. And that one is also squared. Now, this would be meant for an equation, like f of x equals. The only other two things that you'd have to potentially consider, one of them I never talked about with my students, and it doesn't look like it applies to this problem. The other one I always talk about. Confirm that what you're doing is of the proper degree and with a proper sort of, like the things I was going to talk about was regarding your coefficient, your leading coefficient. But confirm that it's of a proper degree. X squared times x squared is x to the 5th power. X to the 5th power is an odd degree function. An odd degree function should either start down and end up or start up and end down. This one starts down and ends up, right? So at least it's an odd degree, at least that matches. But the other thing is, this starts down and ends up. That's what a positive odd degree function does. Make sure this is a positive number. And it is. You don't have to put anything, right? It's a positive 1. One thing that I never did with my students here, and it doesn't apply here, is, see, these actually have scales on their y's. I don't know if this is a positive 1 or a positive 2 or 3 or 20 or whatever. I don't know what it is. If you had a certain y-intercept, like at 8, I could do more things to tell you and help you out with it. And if we run across one of those, I'll do that with you. That's not something I think I'd expect of my students. It's not a kind of problem that I ask them to do. But this is an appropriate one here. I don't know if it's exactly this one. I'm going to assume it is. If they gave us this graph on this software, I assume that it is. All right, there's that one. Let's now graph the following cubic function. Okay, we got another cubic thing to do. I'm going to go very fast on this one here. Well, as fast as I can. We have a reference point center value at -2, -1. This is in that graphing form. So we're at -2, -1 to start right here. I want to focus more on the polynomials of these kinds, not the special ones. All right, -1/3 stretch factor. It means it will go this way. It's flipped over. 1 cubed is 1, but I'm going to take 1/3 of that, and I get 1/3. Ugh. 2 cubed is 8. I'm going to take 1/3 of 8, and I get 8/3. Oh, by the way, 8 down from -1 is -9. It's down here. So 8/3 is 2 2/3. Ugh. So I'm going to go 2 2/3 down. 1, 2, and 2/3 like that. Okay, if you don't love those points, I understand. Let's at least try and get this other point, though. 3 cubed is 27. 1/3 of 27 is 9. Let's go 9 down from -1, and that's at -10. Okay, it's a little off the graph. That's unfortunate. I'll do it on this side, though. 1 1/3, 2 2 2/3, 3 9. 9 again being 1/3 of 27. So 9 up from -1 is 8. Oh, okay, it fits right up there. All right, and here is our cubic. Told you I'd go fast. Oh, except for this part. Da, 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 da. All right, pretty good. Okay. 13 minutes till 3 questions in 13 minutes. Let's do it. We got 1 graph and 2 sketches. We got 3 more graphs. Let's see if we can do them. Oh, it's another cubic. Okay. I don't know. I don't know if I graphed any cubics before. I did cube roots, but not cubics. So I'm actually fine with this. I think I did. Okay. Plus 0, right? We got a center here at 1, 0. So I'm going to start right here. The vertical stretch factor of -2. It will, of course, go downward as well. But this time I will double my heights. Instead of 1, 1, because 1 cubed is 1, I'll go 1, 2. Instead of 2, 8, I would go 2, 16. I'll be honest, I can't fit it. I'm going to plot it way down here just to give you the idea of we shouldn't have our graph go like this because it shouldn't hit x equals 3 until we hit negative 16, right? So it should, keep going down kind of really sharply. And then, these are the kinds of graphs that are really tough for us to do. It's going to be very skinny. But negative 1 comma 2, because again, you're doubling that value right there. And it should go super high before we do anything there. So I'm just going to go down pretty sharp here, like that. And it's really going to bend itself out right there before it comes back down there. I did really curve it, just the point is kind of in the way here. So right here as we go down and super sharp, right, that's where we get down there. All right, these never go fully vertical, right? There is our graph. 49, sketch the following function. There's a negative there, be careful. Negative x squared times x plus 3 times x minus 4. First order of business I would probably do is get those x-intercepts and identify what their multiplicities are. This is an x-intercept of 0. That has a multiplicity of 2 because it's squared. An x-intercept of negative 3, right, it's those opposites, and of 4. Those are multiplicities of 1. So we're going to have an x-intercept here, 0, at negative 3, and at 4. And I'm going to reiterate again here, they scaled our y-axes. When I did these with my classes, we never did, if you see my old videos. So if there was a certain y-intercept, I'd want to be privy to, talk about it. But because the y-intercept is 0 specifically, I guess I don't need to. So that's fine. Okay, negative. This is a negative second degree, third degree, fourth degree, right? X squared times x is negative x to the fourth. It is an even degree, negative leading coefficient. That means it's doing some sort of start down, finish down thing. Now I'm going to go through negative 3 and I'm going to go through 4 linearly. I'm going to go through 0 with a multiplicity thing like this. It's going to bounce off like a parabolic graph. So I'm going to go up and through right here like that. I'm going to go down through 0 and bounce off that thing. Oh, let's just bounce off that thing there. And then I'm going to go down through 4 linearly. And there is a fine graph for this. Kind of not the best, but it's fine. And there we are. That's it. Do we have to do anything else? Graph, sketch? Nope, that's it. Okay. Last problem, number 50. Sketch the following function. Same-ish. Same kind of deals. We didn't get any cubics. Just so you're aware. If this was cubed, it would do something like this. It would go through like a cubic would. This doesn't have any. I just wanted to state that because I don't know what else is going to show up. It's also negative. So we have x-intercepts at 0, negative 4, which has a multiplicity of 2, and at 2, which has a multiplicity of 2. They have those multiplicities because of that quadratic, the squared parts right there. That means they will bounce off of those points. 2s bounce off like quadratics. Cubes go through. They snake through like a cubic. All right. 0 is an x-intercept. Negative 4 is an x-intercept. 2 is an x-intercept. And this is an x times x squared times x squared. That is an x to the 5th. Or a negative, remember, negative x to the 5th. That is an odd degree, which means it'll start up and finish down. I don't know how many times it bounces like this, but it'll start up and it'll finish down. So it goes through negative 4 quadratically, multiplicity of 2. It's going to go through here, bounce off. It's going to go through 0 linearly right here, and it's got to bounce off of 2 to go back down like that. See, it needs to follow that nature, and these bounce offs kind of solidify that thing right there. And that's a fine graph. I don't know how the height thing works. The y-intercept is still 0. I don't have to talk about that. And we are all set. Okay, guys. That ought to do it for this one. This was actually longer. This was actually longer than my 152 or something question integrated math 2 thing. This recording behind me of a basketball game actually fully finished as well. But I hope this stuff here made sense. Down below, right here, I'm sure you finished watching, but in case you need to rewatch anything, down below you have not only timestamps for each problem to be posted in a PDF of this thing if you want to go through it, but also a link to another video where I do more square root and cube root graphs, some where I have a negative square root so the graph ends up going to the left instead of to the right, and then I do some of that Module 11 radical things where you simplify radical expressions and solve radical equations. It's kind of a quick review, but there are some more things there that could gear toward any understanding of all of the material, as this maybe didn't cover all of it. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and I don't know if I'm doing any more recordings through December, but I was glad to have served you here, and I will see you in the next one. Take care.